4.2 light-years from where you sit, a planet orbits a dying ember of a star in conditions so extreme they defy imagination. Scientists called it potentially habitable. Headlines declared it Earth 2.0. Billions of people believed we had found our cosmic backup plan. They were catastrophically wrong. Proxima b is not a sanctuary. It is a world trapped in eternal twilight, bombarded by radiation that would strip the flesh from your bones, locked in gravitational chains that create temperatures ranging from boiling to absolute zero within miles of each other. And between the burning day side and the frozen night side runs a thin line, a boundary so narrow and so hostile that crossing it means death in either direction. For 7 years, humanity has dreamed of reaching this world. The truth about what awaits us there should terrify you. If you want to understand why our nearest potentially habitable exoplanet may be the most dangerous place we have ever discovered, please like and subscribe. Let's begin. The announcement came on August 24th, 2016. Scientists at the European Southern Observatory had detected something extraordinary orbiting our nearest stellar neighbour. After years of painstaking observation and analysis, they confirmed the existence of a rocky world circling Proxima Centauri at a distance that might allow liquid water to exist on its surface. The media erupted. Within hours, headlines proclaimed the discovery of a second Earth. Artists rendered images of blue oceans and green continents basking under the light of a red sun. Space agencies began discussing mission profiles. Entrepreneurs calculated travel times. Humanity collectively exhaled with relief. We had found a backup planet. The timing could not have been more perfect. Climate change dominated global conversations. Political instability spread across continents. Existential anxiety about humanity's future had reached fever pitch. Into this atmosphere of uncertainty dropped news that seemed almost too good to be true. A potentially habitable world existed just 4.24 light-years away, close enough to study in detail, close enough to dream about reaching, close enough to offer hope that our species might not be confined to a single fragile world forever. The scientific paper describing Proxima b landed like a thunderclap in a world desperate for cosmic companionship. Here was concrete evidence that rocky planets existed in habitable zones around other stars. Not just any star, but the closest star to our own sun. Not billions of light-years away in some unreachable corner of the galaxy, but practically next door in astronomical terms. The discovery validated decades of theoretical work suggesting that planets should be common throughout the universe. It confirmed that the conditions necessary for life, at least in terms of orbital distance, could be found throughout our cosmic neighbourhood. But the excitement obscured crucial details that would have terrified anyone who read the fine print. The discovery paper contained warnings that news coverage largely ignored, red flags that astronomers recognized immediately, but that never made it into public consciousness. The world that emerged from careful scientific analysis bore almost no resemblance to the Earth-like paradise that captured public imagination. The gap between scientific communication and public understanding has never been wider than it was in August 2016. Scientists spoke of a planet in the habitable zone, using precise technical language that carried specific meaning within their discipline. Journalists translated this into Earth's twin and second Earth, phrases that conjured images of familiar landscapes under alien skies. The public heard what it wanted to hear: a backup plan, an escape route, a cosmic insurance policy against terrestrial catastrophe. This miscommunication was not malicious. Scientists genuinely believed they had made an important discovery worth celebrating. Journalists genuinely wanted to convey the significance of the finding to general audiences. The public genuinely needed reasons for hope in troubled times. But the result was a collective delusion about what Proxima b actually represented. a delusion that persists in some quarters to this day. Let us begin with what we actually know about Proxima b. The planet orbits its star at a distance of approximately 7.5 million kilometers. This sounds far until you realize that Mercury, the closest planet to our Sun, orbits at 58 million kilometers. Proxima b circles its star at roughly 1/13 the distance between Mercury and the Sun. At such proximity, a year on Proxima b lasts just 11.2 Earth days. The planet completes its entire orbital journey in less time than it takes Earth to rotate 11 times on its axis. Think about what this means for seasonal variation. On Earth, our 365-day orbit creates the rhythm of seasons as our axial tilt changes, which hemisphere receives more direct sunlight. Spring follows winter. Summer follows spring. The cycle of growth and dormancy shapes every ecosystem on our planet. On Proxima b, a full year passes in less than 2 weeks. Whatever seasonal variations exist, if any exist at all, would operate on timescales incomprehensible to Earth-evolved life. This extreme closeness to its parent star exists because Proxima Centauri is not a star like our Sun. It belongs to a class of objects called red dwarfs. These stellar runts represent the most common type of star in our galaxy, comprising roughly 70% of all stars in the Milky Way. When you look up at the night sky, most of the stars you cannot see are red dwarfs. They burn too dimly to be visible to human eyes across interstellar distances, yet they outnumber all other stellar types combined. Red dwarfs burn hydrogen fuel so slowly and so coolly that they can persist for trillions of years. Our Sun will exhaust its fuel in about 5 billion years, swelling into a red giant that will engulf Mercury and Venus and scorch Earth into a cinder. A red dwarf like Proxima Centauri could continue burning for 100 trillion years or more. The universe itself is only 13.8 billion years old. No red dwarf that has ever formed has yet had time to die of old age. They are the tortoises of the stellar world, outlasting their flashier cousins by factors of hundreds or thousands, but this longevity comes at a cost. Red dwarfs produce far less energy than Sun-like stars. Proxima Centauri shines with only about 0.15% of our Sun's luminosity. If you replaced our Sun with Proxima Centauri tomorrow, Earth would freeze solid within days. The amount of energy reaching our planet would drop by a factor of nearly 700. The oceans would become ice. The atmosphere would begin condensing. Complex life would perish almost immediately. To receive the same amount of energy that Earth receives from the Sun, a planet would need to orbit a red dwarf at extremely close range. The physics is straightforward. Less luminous stars require closer orbits to maintain habitable temperatures. The habitable zone around Proxima Centauri begins at roughly 4 million kilometers and extends to about 30 million kilometers. Compare this to our solar system, where the habitable zone spans from about 130 million kilometers to roughly 250 million kilometers. The habitable zone around a red dwarf is not just closer to the star. It is dramatically narrower. Proxima b sits squarely within this zone at 7.5 million kilometers. This orbital distance places it almost exactly in the middle of the region, where liquid water could theoretically exist on a planetary surface. From a purely geometric standpoint, the planet occupies prime real estate. The media amplified it into certainty about habitability, but scientists define the habitable zone as the region around a star where liquid water could theoretically exist on a planetary surface. This concept sounds straightforward but contains hidden complexities that prove crucial for understanding. Proxima b. The habitable zone represents a necessary but not sufficient condition for habitability. Many factors beyond orbital distance determine whether a world can support life as we know it. The habitable zone concept emerged in the 1950s and 60s as astronomers began seriously considering the possibility of life beyond Earth. Early definitions focused purely on temperature. If a planet receives enough stellar energy to keep water liquid but not so much that water boils away, it falls within the habitable zone. This simple thermal criterion provided a useful first approximation for identifying potentially interesting worlds, but decades of planetary science have revealed how inadequate this simple definition truly is. Venus orbits within or near the inner edge of our solar system's habitable zone, yet its surface temperature exceeds 460 degrees Celsius due to a runaway greenhouse effect. Mars orbits within or near the outer edge of the habitable zone, yet its thin atmosphere and lack of magnetic field have rendered it a frozen desert. Both worlds demonstrate that orbital distance alone does not guarantee habitability. The modern understanding of habitable zones incorporates atmospheric composition, planetary mass, magnetic field strength, stellar activity, and dozens of other factors. A planet can orbit at the perfect distance from its star and still be completely uninhabitable due to conditions that orbital position cannot predict. The habitable zone is better understood as a zone of possibility rather than a zone of habitability. It identifies worlds worth studying further, not worlds guaranteed to support life. The Discovery team estimated Proxima B's mass at approximately 1.3 times Earth's mass. This makes it a super-Earth, a classification that sounds promising but tells us almost nothing about surface conditions. A planet 1.3 times Earth's mass could be a rocky world with a thin atmosphere, similar to a larger version of Earth. It could be a water world covered in global oceans, hundreds of kilometers deep, with no solid surface at all. It could be a mini Neptune, shrouded in crushing hydrogen and helium atmospheres that would annihilate any Earth-like life instantly. The detection method used to find Proxima b reveals mass but not composition. Mass alone provides almost no constraint on what a planet actually looks like. Consider objects in our own solar system. Mercury, Earth, and Mars are all rocky worlds with solid surfaces, yet their masses span a range of nearly 20 to 1. Venus and Earth have almost identical masses, yet possess radically different surface conditions. Mass tells you how much stuff a planet contains, not how that stuff is arranged or what conditions exist at the surface. Astronomers discovered Proxima b using the radial velocity method. This technique detects planets by measuring the tiny wobble they induce in their parent stars. As a planet orbits, its gravity tugs the star back and forth. The planet and star actually orbit a common center of mass, with both bodies moving in response to their mutual gravitational attraction. For a system like Proxima Centauri and Proxima b, the star's motion is tiny but detectable with modern instruments. Sensitive spectrographs can detect stellar motion as periodic shifts in the star's light spectrum. When it moves away, the light is redshifted as wavelengths stretch. By measuring these shifts over time, astronomers can calculate the period and amplitude of the stellar wobble, which reveals the orbital period and minimum mass of any orbiting planet. The radial velocity method has discovered hundreds of exoplanets since the first confirmed detection in 1995. It works best for massive planets orbiting close to their stars, which produce larger and more frequent stellar wobbles. A Jupiter-sized planet in a tight orbit makes its star visibly wobble. An Earth-sized planet in a distant orbit produces a wobble, barely distinguishable from instrumental noise. Proxima b represents an ideal target for radial velocity detection. Its close orbit means it completes many orbits in a short observation period, making the periodic signal easier to identify. Its relatively high mass produces a measurable stellar wobble. The confirmation of its existence required observing Proxima Centauri over multiple years and combining data from several different instruments. But the signal eventually emerged clearly from the noise. However, the radial velocity method provides orbital parameters and minimum mass estimates, but cannot directly image the planet or analyze its atmosphere. The technique reveals that something is pulling on the star with a certain period and strength. It cannot show what that something looks like, what its surface conditions might be, or whether it possesses the atmospheric characteristics necessary for life. Everything we think we know about Proxima b's surface comes from theoretical models and educated guesses. No telescope has ever photographed this world. No instrument has ever detected its atmosphere. no spacecraft has ever visited the Proxima Centauri system. The inviting images of oceans and continents that accompanied news coverage were artistic fantasies, not scientific observations. This distinction between detection and characterization matters enormously for understanding what Proxima b represents. We know the planet exists. We know its orbital period. We know its minimum mass. We know essentially nothing else with certainty. The blue-green world depicted in media coverage was an artist's imagination, not a scientist's observation. The assumption of Earth-like conditions was a projection of human hopes, not a conclusion from data. But let us assume the optimistic scenario. Let us grant that Proxima b has a rocky surface, an atmosphere, and liquid water. Let us imagine that all the unknown factors broke in favor of habitability. Even under these generous assumptions, the planet faces challenges that would make Earth life impossible. The first problem is stellar radiation. Our Sun bombards Earth with electromagnetic energy across a wide spectrum. Most of this radiation falls within visible light frequencies that our atmosphere handles easily. Visible light passes through air without significant absorption, which is why we can see the sun and stars. Our atmosphere blocks more dangerous wavelengths while transmitting the relatively benign energy that drives photosynthesis and warms our world. Earth's magnetic field provides another layer of protection. Generated by convection currents in our planet's liquid iron core, the magnetic field extends far into space and deflects the charged particles streaming from the sun in the solar wind. Without this magnetic shield, the solar wind would gradually strip away our atmosphere and bombard the surface with damaging radiation. Mars lost most of its atmosphere after its magnetic field collapsed billions of years ago, demonstrating what happens to unshielded worlds. Our ozone layer adds a third protective system. Ozone molecules in the upper atmosphere absorb harmful ultraviolet radiation before it reaches the surface. This absorption prevents the molecular damage that ultraviolet light causes to biological structures. Life on Earth evolved under ozone protection and remains vulnerable to ultraviolet exposure. The ozone hole discovered in the 1980s prompted international action precisely because increased ultraviolet radiation poses serious health risks. These multiple protective systems work together to create the relatively benign radiation environment that allowed complex life to evolve. Earth is not radiation-free, but the radiation that reaches our surface falls within limits that biology can handle. Our cells possess repair mechanisms that fix radiation damage faster than it accumulates under normal conditions. Evolution has had billions of years to optimize these repair systems under Earth's particular radiation regime. Proxima Centauri operates completely differently. Red dwarfs emit most of their energy in infrared wavelengths rather than visible light. A human standing on Proxima b would perceive a dim, reddish environment, quite unlike the bright white light of Earth's sunny days. The overall illumination might resemble perpetual sunset, with colors shifted toward the red end of the spectrum and shadows appearing deeper and more pronounced than under solar illumination. But the chronic radiation output represents only part of the story. The real danger lies in the episodic events that make Proxima Centauri one of the most violent stars in our cosmic neighborhood. Red dwarfs are notorious flare stars. They experience sudden, explosive releases of energy that dwarf anything our sun produces. Our sun does produce flares, sudden brightenings associated with magnetic reconnection events in the solar atmosphere. But solar flares represent minor perturbations in an otherwise stable energy output. They can disrupt radio communications and damage satellites, but pose no direct threat to surface life on Earth. Proxima Centauri's flares operate on an entirely different scale. In 2019, astronomers detected a superflare from Proxima Centauri that released more energy in 10 seconds than our Sun produces in typical flares. This single event increased the star's brightness by a factor of 14,000 in ultraviolet wavelengths. The energy release would have bathed any nearby planet in radiation levels sufficient to sterilize exposed surfaces almost instantaneously. If Earth orbited at Proxima b's distance from such a star, this flare would have delivered a lethal dose of radiation to any unprotected surface. Not merely dangerous, not merely harmful, lethal. The ultraviolet flux alone would have been sufficient to break apart biological molecules, destroy cell membranes, and denature proteins within seconds of exposure. But that superflare was not exceptional. Proxima Centauri experiences major flares approximately once per day. Smaller flares occur constantly, creating a baseline of elevated radiation that never subsides to safe levels. The planet we celebrated as potentially habitable orbits within a radiation environment that would be lethal to any Earth-based organism. The mechanism behind red dwarf flares relates to their internal structure. Unlike our Sun, which has a radiative core surrounded by a convective outer layer, red dwarfs are fully convective. Material circulates from the core to the surface and back in continuous currents. This convection generates powerful magnetic fields that become tangled and stressed over time as different stellar latitudes rotate at different speeds. When these magnetic tangles snap and reorganize, they release tremendous energy in the form of flares and coronal mass ejections. Coronal mass ejections represent an even greater threat than flares. These events blast billions of tons of charged particles into space at speeds approaching significant fractions of light speed. When a coronal mass ejection strikes a planet, it can strip away atmospheric gases, erode surface water, and damage any magnetic field the planet might possess. Earth's magnetic field deflects most coronal mass ejection material, channeling it toward the poles where it creates auroras. A planet without a strong magnetic field would experience direct atmospheric erosion from every major stellar event. Studies of Proxima B's radiation environment paint a bleak picture. The planet receives approximately 400 times more X-ray radiation than Earth receives from the Sun. It experiences roughly 2,000 times more extreme ultraviolet flux. These numbers represent averages over time, incorporating both quiet periods and flare events. During major flares, the radiation levels spike to values that almost defy comprehension. Over billions of years, this relentless bombardment would likely strip away any atmosphere the planet might have possessed at formation. The constant stream of high-energy particles and photons would accelerate atmospheric molecules to escape velocity, bleeding the atmosphere into space one molecule at a time. Even if Proxima b formed with an Earth-like atmosphere, it has had 4 to 7 billion years to lose that atmosphere to stellar activity. But let us continue assuming optimistically. Perhaps Proxima b formed with an extraordinarily thick atmosphere that could withstand stellar erosion. Perhaps it possesses a powerful magnetic field generated by a molten iron core like Earth's. Perhaps volcanic activity continuously replenishes lost atmospheric gases. Perhaps some combination of factors allowed it to retain an atmosphere despite the constant assault from its parent star. Even granting these assumptions, we encounter the second major problem that makes Proxima b almost certainly uninhabitable. Tidal locking. When a planet orbits close to its star, gravitational interactions gradually slow its rotation. The star's gravity tugs more strongly on the near side of the planet than on the far side. This differential tug creates a torque that acts to slow the planet's rotation over time. Over millions or billions of years, the planet's rotation period becomes synchronized with its orbital period. The planet ends up with one hemisphere permanently facing the star and one hemisphere permanently facing away. This configuration is called tidal locking, and it creates conditions unlike anything in our solar system. Our moon is tidally locked to Earth, which is why we always see the same lunar face. But the moon receives sunlight from all directions over the course of its orbit, preventing the extreme temperature differences that tidal locking to a star would create. A planet tidally locked to its star experiences something far more extreme. Earth rotates on its axis once every 24 hours. Every location on our planet experiences day and night in regular cycles. This rhythm distributes solar energy relatively evenly across our globe, preventing either hemisphere from reaching thermal extremes. The temperature difference between Earth's equator and poles measures roughly 100 degrees Celsius. A tidally locked planet experiences something radically different. One hemisphere bakes under constant stellar illumination. The star hangs fixed in the sky, never rising, never setting. The same surface regions receive energy input continuously, with no night to provide cooling. The other hemisphere freezes in permanent darkness. No stellar energy ever reaches the dark side, which radiates heat into space until temperatures approach the cosmic background level. The temperature difference between these hemispheres can exceed several hundred degrees Celsius depending on atmospheric properties. Scientists who model tidally locked planets describe nightmarish scenarios that bear no resemblance to any environment on Earth. On the day side, surface temperatures could exceed the boiling point of water. Beneath the star's eternal gaze, rocks heat until they glow with thermal radiation. Any water present boils away, adding steam to an already hostile atmosphere. A substellar point, directly beneath the star, receives the most intense heating. Moving away from this point in any direction brings gradually decreasing temperatures but never brings darkness. On the night side, temperatures plunge toward absolute zero. Without stellar input, the surface radiates heat into space with nothing to replace it. Water freezes solid. Atmospheric gases might condense and precipitate as frozen deposits. Nitrogen and oxygen could literally snow out of the air, accumulating in drifts on the eternal dark side. The antistellar point, exactly opposite the substellar point, would be the coldest location on the planet. Between these extremes runs a thin band called the terminator zone. This boundary region, separating permanent day from permanent night, represents the only location where temperatures might remain moderate enough for liquid water. Some scientists have proposed that life could exist in this twilight strip, sheltered from both the burning day side and the frozen night side, but the terminator zone faces its own challenges. Atmospheric models predict howling winds, rushing from the day side to the night side, as hot air expands and cold air contracts. The pressure differential between the two hemispheres drives atmospheric circulation at extreme velocities. These winds could exceed hundreds of miles per hour, creating a permanent hurricane that circles the planet along the terminator line. No surface feature could withstand such constant erosion. Any landforms that developed would be sandblasted into oblivion over geological time. Any structures that organisms might build would face continuous assault from atmospheric violence. The terminator zone is not a peaceful twilight haven. It is a battleground between thermal extremes. Additionally, the terminator zone measures only tens of kilometers wide on a planetary scale. This narrow strip would need to maintain stable temperatures, despite being sandwiched between radically different thermal environments. Any slight wobble in the planet's axis, any variation in stellar output, could shift the terminator zone and destabilize whatever conditions had developed there. The combination of extreme radiation, tidal locking, and atmospheric stripping creates a world fundamentally hostile to life as we understand it. Yet Proxima b continues to capture public imagination as a potential second home for humanity. This disconnect between scientific reality and popular perception reveals something important about how we process cosmic information. Humans evolved on Earth. Our intuitions about planetary environments derive from experience on this particular world. When we hear that a planet orbits within the habitable zone, our minds automatically populate it with familiar features. Blue skies, green plants, breathable air, comfortable temperatures. We cannot help but project earthly conditions onto alien worlds, but the universe does not care about human comfort. The habitable zone represents a narrow band of possibility, not a guarantee of habitability. A planet can orbit within the zone while possessing surface conditions that would kill any Earth organism instantly. Proxima b almost certainly represents such a world. The discovery announcement in 2016 emphasized the positive aspects of the finding. Scientists are trained to present findings accurately, but headlines are written to attract attention. The phrase potentially habitable conveyed scientific caution and appropriate uncertainty. The phrase "Earth's twin" conveyed journalistic excitement and premature certainty. Public understanding followed the headlines, not the caveats. 7 years later, we know considerably more about Proxima Centauri and the challenges facing any world in its vicinity. The initial optimism has given way to a more sober assessment. Proxima b almost certainly cannot support life on its surface. Any life that might exist would need to shelter underground or within subsurface oceans, shielded from the radiation and temperature extremes that characterize the planet's exposed regions. But even subsurface habitability faces severe challenges. The energy sources that drive subsurface ecosystems on Earth ultimately derive from geological activity and chemical gradients. Proxima b may lack the internal heat necessary to maintain geological activity over billions of years. Without ongoing volcanism or hydrothermal activity, the chemical energy that subsurface life requires may simply not exist. The discovery still matters despite these sobering realities. Proxima b demonstrated that rocky planets exist in habitable zones around nearby stars. It showed that our cosmic neighborhood contains worlds worth studying, even if they cannot serve as backup homes for humanity. Most importantly, it revealed the gap between what we hope to find and what nature actually provides. The universe is not obligated to give us what we want. It offers only what physics allows. Understanding this distinction represents the first step toward genuine cosmic awareness. Proxima b taught us that the nearest habitable zone planet might not be habitable at all. The planet that captured our imagination as a potential refuge has turned out to be a hell world wrapped in cosmic proximity. The promise that fooled a planet was not a lie, it was a misunderstanding. Scientists discovered exactly what they announced: a rocky planet in the habitable zone of the nearest star. The public heard something different: a second Earth waiting to receive human colonists. The gap between these interpretations has taken years to close and remains incompletely bridged even now. Proxima b exists. It orbits in the habitable zone. These facts remain true and scientifically significant. But the planet that exists bears no resemblance to the paradise that media coverage depicted. The habitability that scientists cautiously suggested has been largely ruled out by subsequent research. The backup planet that humanity celebrated has turned out to be a radiation-blasted, tidally locked nightmare. The next sections will explore these challenges in devastating detail. The star that seemed promising reveals itself as a stellar monster. The twilight zone that offered hope reveals itself as an atmospheric battleground. The distance that seemed achievable reveals itself as an unbridgeable gulf. Proxima b is not what you think, and understanding what it actually is requires confronting realities that no headline has adequately conveyed. Imagine standing on a beach watching the sunrise. The horizon glows orange and red as our sun climbs into view. Within minutes, full daylight arrives. The star that has nurtured life on Earth for nearly 4 billion years delivers its steady, reliable energy. This scene repeats every morning across our planet. Humanity takes solar stability for granted because we have never known anything else. Our sun rises and sets with clockwork precision. Seasons change as Earth's axial tilt shifts, which hemisphere receives more direct illumination. But the total energy output of our star varies by less than 0.1% over its 11-year activity cycle. This stability has persisted for billions of years and will continue for billions more. Life on Earth evolved under a cosmic heat lamp so reliable that organisms could develop exquisite sensitivity to tiny variations in light and temperature. The difference between summer and winter feels dramatic to us. In cosmic terms, it represents barely a flicker. Now imagine a different sunrise. The star emerging over the horizon glows deep crimson, casting ruddy light across an alien landscape. It appears larger than our sun because the planet orbits so close. Perhaps 2.5 times the angular diameter of the sun as seen from Earth. The light feels different, dimmer in some ways, saturated with wavelengths that human eyes struggle to process. Colors appear strange. Reds dominate while blues fade into murky shadows. The overall illumination resembles a perpetual sunset on Earth. That golden hour that photographers prize, except it never brightens beyond this dusky glow. Then, without warning, the star erupts. Its brightness increases by a factor of thousands in seconds. The dim red orb transforms into a blazing beacon that overwhelms adapted eyes. Invisible radiation, sleeting through the atmosphere, begins breaking apart molecules. The sky takes on a purple hue. As atmospheric gases fluoresce under bombardment, nitrogen and oxygen atoms, absorbing high-energy photons and re-emitting visible light in colors no Earth atmosphere has ever displayed, any exposed organic material begins to break down at the molecular level. Proteins denature. DNA strands shatter. Cell membranes rupture as the radiation deposits energy faster than any repair mechanism can compensate. This is not science fiction. This is the confirmed reality of existence near Proxima Centauri, the star that seemed so promising when astronomers announced Proxima B's discovery, is actually one of the most hostile stellar environments in our local cosmic neighborhood. Understanding why requires examining what red dwarfs truly are and how they differ from the stable, nurturing star that made Earth possible. Red dwarfs occupy the bottom of the stellar mass range. Stars form when clouds of hydrogen gas collapse under their own gravity, compressing and heating until nuclear fusion ignites in the core. The minimum mass required to achieve sustained fusion is approximately 8% of our Sun's mass. Below this threshold, objects cannot generate enough core pressure and temperature to fuse hydrogen into helium continuously. They become brown dwarfs, failed stars that glow only from the gravitational energy released during their initial contraction. Above the 8% threshold, true stars are born. But not all stars are created equal. The mass of a star determines almost everything about its behavior: its temperature, its luminosity, its lifespan, its stability. More massive stars burn hotter and brighter but exhaust their fuel quickly. Less massive stars burn cooler and dimmer, but can persist for astronomical eternities. Our Sun, a yellow dwarf with one solar mass by definition, represents a middle ground. It has enough mass to burn brightly, but not so much that it consumes itself rapidly. Red dwarfs represent the low-mass extreme of true stellar objects. They range from approximately 8% to roughly 50% of solar mass. Within this range, Proxima Centauri sits toward the lower end, containing roughly 12% of our Sun's mass. This makes it a relatively substantial red dwarf compared to the smallest examples, but still tiny compared to Sun-like stars. If our Sun were a basketball, Proxima Centauri would be roughly the size of a tennis ball. The mass difference is even more dramatic than the size comparison suggests. This low mass produces low core temperatures. Nuclear fusion rates depend exponentially on temperature. A small decrease in core temperature produces a large decrease in energy output. Proxima Centauri's core reaches temperatures of only about 4 million Kelvin compared to our Sun's 15 million Kelvin. This cooler core supports much slower fusion reactions, which in turn produces far less energy. The surface temperature difference tells the same story. Proxima Centauri's photosphere measures approximately 3050 Kelvin compared to our Sun's 5778 Kelvin. This temperature difference determines the color of starlight. Hotter stars emit more blue light, cooler stars emit more red light. Proxima Centauri glows deep red because its surface is nearly 3000 degrees cooler than our Sun's. The luminosity difference is even more dramatic. Proxima Centauri shines with only about 0.15% of our Sun's total energy output, less than 2/1000ths of the light and heat that our star produces. If you could instantly swap Proxima Centauri for our Sun, keeping everything else the same, Earth would receive less than 1/500th of its current solar energy. Our oceans would freeze within days. Our atmosphere would begin condensing within weeks. complex life would perish almost immediately, with only the hardiest extremophiles surviving temporarily in geothermally heated refuges. But low mass creates something beyond mere dimness. It creates instability. The internal structure of red dwarfs differs fundamentally from sun-like stars in ways that have profound implications for any planets orbiting nearby. Our Sun has a layered architecture that results from how energy moves through its interior. The core where fusion occurs sits at the center, generating energy through the proton-proton chain reaction that converts hydrogen into helium. This energy must somehow travel from the core to the surface, but the journey is not straightforward. Surrounding the core lies a radiative zone, where energy travels outward through photon absorption and re-emission. A photon generated in the core gets absorbed by a nearby atom, which then re-emits a photon in a random direction. This random walk continues for hundreds of thousands of years as energy gradually diffuses toward the surface. The radiative zone is so dense that photons cannot travel far before being absorbed. Energy moves through this region, not by physical motion of material but by the slow diffusion of electromagnetic radiation. Above the radiative zone lies a convective zone, where hot material physically rises while cooler material sinks. In this outer third of the Sun, energy travels primarily through bulk fluid motion rather than radiation. Hot plasma rises toward the surface, releases its energy, cools, and sinks back down to be reheated. This convection creates the granulated appearance of the Sun's surface, where each granule represents the top of a convective cell. The boundary between the radiative and convective zones, called the tachocline, plays a crucial role in generating our Sun's magnetic field. The differential rotation between these two zones, with the radiative interior rotating as a solid body, while the convective exterior rotates differently at different latitudes, creates shearing forces that stretch and amplify magnetic field lines. This process generates the Sun's 11-year activity cycle and its relatively stable magnetic behavior. Red dwarfs lack this layered structure entirely. They are convective throughout. Material from the core rises directly to the surface and sinks back down in continuous currents that span the entire star. There is no radiative zone. There is no tachocline. The whole star convection operates under completely different dynamics than the partial convection in Sun-like stars. This whole star convection has profound implications for magnetic activity. As conducting plasma circulates through the stellar interior, it generates magnetic fields through the dynamo effect. Moving charged particles create magnetic fields. Magnetic fields exert forces on charged particles. The interaction between plasma flow and magnetic fields becomes incredibly complex in a fully convective star where material circulates from core to surface continuously. The more vigorously material circulates, the stronger the magnetic fields become. Red dwarfs, despite their small size and low energy output, generate magnetic fields far more intense than our Sun produces. Some red dwarfs possess surface magnetic fields thousands of times stronger than the Sun's average field strength. This intense magnetism arises directly from the whole star convection that characterizes these diminutive stellar objects. Sun-like stars possess relatively stable magnetic fields because only part of their interior participates in convection. The radiative zone acts as a buffer, moderating the magnetic dynamics and creating the predictable 11-year cycle that characterizes our Sun's behavior. Solar activity waxes and wanes, but within well-understood limits. The Sun has never produced a flare that threatened life on Earth's surface. Even the largest recorded solar events, like the Carrington event of 1859, affected only electromagnetic infrastructure while leaving biological systems unharmed. Red dwarfs possess intensely variable magnetic fields because their entire mass participates in the convective dynamo. Without a stabilizing radiative zone, magnetic activity can fluctuate wildly and unpredictably. The magnetic fields become twisted and tangled by differential rotation as different latitudes of the star rotate at different speeds. This differential rotation stretches field lines, amplifying their strength while creating increasingly unstable configurations. Eventually, the tangled field lines snap and reconnect, releasing tremendous energy in the process. The physics resembles what happens when you twist a rubber band past its breaking point. Energy stored in the magnetic field configuration converts suddenly into kinetic energy, thermal energy, and electromagnetic radiation. Material accelerates to enormous velocities. Temperatures spike to millions of degrees. Radiation floods outward across the electromagnetic spectrum. This is a stellar flare, and red dwarfs experience them constantly. The frequency and intensity of red dwarf flares exceeded anything astronomers predicted when they first began studying these stars systematically. Our Sun produces flares, but solar flares are minor perturbations in an otherwise stable energy output. The largest solar flares release energy equivalent to billions of hydrogen bombs, which sounds impressive until you realize how small that is compared to the Sun's total output. A major solar flare represents roughly 1/10,000,000,000th of the Sun's luminosity integrated over the flare duration. Red dwarf flares operate on completely different scales. A major flare from a red dwarf can increase the star's total brightness by factors of hundreds or thousands. The energy released in seconds or minutes can exceed what the star normally produces over entire days. These events transform dim, barely visible stars into brilliant beacons visible across vast cosmic distances. The largest flares from Proxima Centauri would be catastrophic by any measure. In March 2016, just months before the Proxima b announcement that captured the world's imagination, the star produced a flare that increased its brightness by 68 times in visible wavelengths. From the dim red ember that humans cannot see with naked eyes, Proxima Centauri briefly became a star visible to unaided observers had anyone known where to look. In ultraviolet wavelengths, where the damage to biological systems is most severe, the increase exceeded a factor of 1,000. The energy released during this single event equaled a significant fraction of what Proxima Centauri normally produces in an entire day, concentrated into minutes rather than hours. This energy created radiation intensities that no Earth organism could survive without shielding. Any life on the surface of Proxima b during this flare would have experienced radiation exposure equivalent to standing inside a nuclear reactor core, but that March 2016 flare paled in comparison to what astronomers detected on May 1, 2019. A team using multiple observatories across different wavelength ranges captured a superflare that represented the most extreme event ever recorded from Proxima Centauri. The star brightened by 14,000 times in ultraviolet wavelengths over a period of just 10 seconds. Not 14,000%, 14,000 times. The ultraviolet output increased by a factor larger than the total luminosity ratio between our Sun and Proxima Centauri. The total energy release exceeded 10 to the 31st joules. This number defies human comprehension, so let us translate it into more familiar terms. 10 to the 31st joules is roughly comparable to the output of 100 billion nuclear warheads detonating simultaneously. It exceeds the total energy consumption of human civilization throughout all of history by factors of millions. It represents a significant fraction of the energy our Sun produces in an entire second, concentrated into a burst lasting less than a minute. Proxima b sits 7.5 million kilometers from this stellar bomb. When the superflare occurred, it bathed the planet in radiation levels that would prove instantly lethal to any known Earth organism. The ultraviolet flux alone would have been sufficient to break apart biological molecules, destroy cell membranes, and denature proteins within seconds of exposure. Any life on the surface would have died before it could seek shelter, before it could recognize the danger, before nerve impulses could travel from sensory organs to brain. The X-ray flux would have penetrated deeper, damaging organisms underground or underwater that might have survived the ultraviolet burst. High-energy particles accelerated by the flare would have arrived minutes later, delivering additional radiation doses to anything that had somehow survived the initial electromagnetic pulse. The surface of Proxima b during this event would have resembled the inside of a sterilization chamber more than a habitable world. But the superflare was not a one-time event. It was a particularly dramatic example of ongoing stellar behavior that characterizes Proxima Centauri continuously. Studies monitoring the star over extended periods have revealed that significant flares occur roughly once per day. Smaller events occur even more frequently, creating a baseline of elevated radiation that never subsides to truly quiet levels. The planet exists in a constant state of bombardment, never knowing when the next sterilizing blast might arrive. Imagine trying to survive on a world where lethal radiation bursts occur daily, where any moment might bring a flare that destroys everything exposed to starlight, where the warning time between flare onset and lethal exposure measures in seconds rather than hours or days. This is the reality of Proxima b. The mechanism of flare damage extends beyond simple heating, though the heating itself would be catastrophic. When Proxima Centauri flares, it emits radiation across the electromagnetic spectrum, from radio waves through visible light to X-rays and beyond. Each wavelength range interacts with matter differently, creating multiple pathways for damage. Radio waves and infrared radiation deposit energy as heat. During major flares, this heating can raise surface temperatures by tens or hundreds of degrees within minutes. Any liquid water exposed to the sky would begin boiling. Any organisms adapted to specific temperature ranges would experience lethal thermal shock. But the heating effects are almost gentle compared to what higher energy radiation does. Visible light during a flare increases dramatically but poses primarily a brightness hazard. Any organisms with visual systems would be blinded temporarily or permanently. Photosynthetic organisms might experience damage to their light harvesting systems, but visible light lacks the energy to break chemical bonds directly. It interacts with matter through electronic excitation rather than ionization. The most dangerous emissions fall in the extreme ultraviolet and X-ray ranges. These high-energy photons carry enough energy to ionize atoms and break molecular bonds. When extreme ultraviolet radiation strikes an oxygen molecule, it can strip away electrons and split the double bond holding the two oxygen atoms together. The oxygen atoms that result are highly reactive free radicals. They combine with other molecules in ways that alter atmospheric chemistry fundamentally. Over time, this photochemical damage can destroy ozone layers, produce toxic compounds like nitrogen oxides and hydrogen peroxide, and fundamentally change the composition of planetary atmospheres. Earth's ozone layer regenerates because our sun's ultraviolet output remains within limits that atmospheric chemistry can handle. Proxima b receives ultraviolet fluxes that would destroy ozone faster than any conceivable regeneration mechanism could replace it. X-rays penetrate even deeper into matter than ultraviolet radiation. They can pass through thin atmospheres with minimal absorption and deliver their energy directly to planetary surfaces. When X-rays encounter biological molecules, they cause ionization damage that represents the most dangerous form of radiation exposure for living systems. The mechanism works like this. An X-ray photon strikes a molecule and transfers its energy to an electron, ejecting that electron from its atomic orbital. This creates an ion, an electrically charged species that is highly reactive. If the ionization occurs within a DNA molecule, it can break the sugar phosphate backbone, creating single-strand or double-strand breaks. If it occurs within a protein, it can alter the three-dimensional structure that gives the protein its function. DNA strand breaks are particularly dangerous because DNA carries the genetic information necessary for life. Single-strand breaks can often be repaired by cellular machinery, using the intact complementary strand as a template. Double-strand breaks are much more dangerous, often leading to chromosomal aberrations or cell death. The radiation levels during a Proxima Centauri superflare would create double-strand breaks faster than any known repair mechanism can fix them. Proteins misfold when radiation damages the bonds holding them in their functional configurations. Enzymes lose their catalytic activity. Structural proteins lose their mechanical properties. Cell membranes become leaky as membrane proteins fail. The entire molecular machinery of life degrades under radiation bombardment. Even organisms with radiation resistance far exceeding anything on Earth would struggle to survive chronic X-ray exposure at the levels Proxima b experiences. The most radiation-resistant organism known, Deinococcus radiodurans, can survive acute radiation doses roughly 1,000 times higher than what kills a human. But Deinococcus achieves this resistance through extraordinarily efficient DNA repair mechanisms that require time and energy to function. Under continuous bombardment that creates damage faster than repair can occur, even this extremophile would eventually succumb. But the radiation damage from flares represents only part of the threat facing Proxima b. Flares are often accompanied by coronal mass ejections, events that pose a different but equally serious danger to planetary habitability. A coronal mass ejection occurs when magnetic reconnection events accelerate. Billions of tons of charged particles, primarily protons and electrons torn from hydrogen atoms, blast away from the stellar surface at speeds approaching significant fractions of light speed. This particle storm races outward through the star system, carrying magnetic fields frozen into the plasma like threads in a fluid. When a coronal mass ejection strikes a planet, it interacts with any magnetic field present and any atmosphere remaining. The interaction can be gentle or catastrophic, depending on the planet's defenses. Earth's magnetic field provides robust protection against solar coronal mass ejections. The magnetosphere deflects most charged particles, channeling them toward the polar regions where they create auroras. The beautiful northern and southern lights represent successful defense against potentially harmful radiation. Particles that would damage atmospheric ozone and threaten surface life instead excite oxygen and nitrogen atoms high in the atmosphere, producing the shimmering colored lights that have inspired human wonder for millennia. But Earth's magnetic field developed because our planet has a large, liquid iron core that generates a global dynamo. The convective motions of conducting liquid iron create electric currents that generate magnetic fields. These fields extend far into space, creating a protective bubble around our world that deflects the solar wind and most coronal mass ejection material. Not all planets can maintain such protection. Smaller planets may lack the internal heat to maintain liquid cores. Their iron may have solidified long ago, shutting down the dynamo that generates protective magnetic fields. Mars appears to have lost its global magnetic field billions of years ago, retaining only localized crustal magnetism that provides minimal protection against solar activity. Planets tidally locked to their stars may experience reduced internal dynamics that weaken magnetic field generation. The same gravitational forces that lock one face toward the star also affect internal convection patterns. Tidal heating can provide energy input, but the geometry of the heating may not support the large-scale circulation needed for an effective dynamo. Whether Proxima b possesses a significant magnetic field remains unknown. We cannot measure planetary magnetic fields across interstellar distances with current technology, but theoretical models suggest that a planet of Proxima b's size and orbital configuration may struggle to maintain the internal dynamics necessary for strong magnetic field generation. If Proxima b lacks a significant magnetic field, then coronal mass ejections strike its atmosphere directly. The consequences would be catastrophic over geological timescales. The charged particles in a coronal mass ejection carry tremendous kinetic energy. When they collide with atmospheric molecules, they transfer this energy through a process called sputtering. The collision can accelerate atmospheric molecules to velocities exceeding the planet's escape velocity. These molecules then drift away into space, never to return. Gas literally bleeds away from the planet with every coronal mass ejection impact. The rate depends on the intensity of stellar activity, the density of the atmosphere, and the mass of atmospheric molecules. Lighter gases like hydrogen and helium escape most easily. Heavier gases like nitrogen and carbon dioxide resist escape better, but still face erosion under sufficiently intense bombardment. Over billions of years, this process can strip a planet completely bare. Mars demonstrates the endpoint of atmospheric loss. Whatever thick atmosphere Mars possessed in its youth has eroded away, leaving a surface pressure less than 1% of Earth's. The Martian atmosphere is too thin to support liquid water at most surface temperatures. Any water present sublimes directly from ice to vapor. Models suggest that Proxima b has likely lost significant atmospheric mass to stellar activity. The planet is 4 to 7 billion years old, meaning it has endured the red dwarf's violent behavior since the formation of the Proxima Centauri system. Billions of years of flares and coronal mass ejections would have removed atmosphere equivalent to several Earth atmospheres. Assuming the planet possessed such an atmosphere initially, the loss rate accelerates during the early history of planetary systems. Young red dwarfs are even more active than their older counterparts. The same convective dynamics that generate magnetic activity operate more vigorously in younger stars with faster rotation rates. A young red dwarf can produce flares 10 to 100 times more frequently and more energetically than the same star produces in its old age. During Proxima Centauri's first billion years, stellar activity likely exceeded current levels by enormous factors. Any primordial atmosphere that Proxima b possessed would have faced a brutal gauntlet of radiation exposure during precisely the period when atmospheric retention matters most for long-term habitability. On Earth, the first billion years saw the origin of life and the development of early ecosystems. While stellar bombardment during the late heavy bombardment period stressed early life, our Sun's relatively stable output allowed atmospheric chemistry to reach equilibrium. The gases released by volcanoes and comets accumulated, rather than being stripped away. Earth's atmosphere grew over time rather than shrinking. Proxima b faced the opposite trajectory. Whatever atmosphere it possessed at formation began eroding immediately. The erosion rate decreased as the star aged and became less active. But by then, significant atmospheric mass would have been lost. The planet we observe today, billions of years after formation, has endured a continuous assault that Earth never experienced. The implications extend beyond atmospheric loss to the fate of water. Water, which we prize as essential for life, presents particular challenges in the Proxima b environment. The chemistry of water loss involves multiple pathways that all operate more efficiently around active red dwarfs than around stable sun-like stars. Water molecules in the upper atmosphere absorb ultraviolet radiation and undergo photodissociation. A high-energy photon strikes a water molecule and breaks the bonds holding the two hydrogen atoms to the oxygen atom. The products are hydrogen atoms and hydroxyl radicals. The hydrogen atoms, being extremely light, can easily achieve escape velocity through thermal motion alone. They drift away into space, lost forever. The oxygen atoms face a different fate. They are too heavy to escape easily but too reactive to remain as free atoms. They combine with other molecules, forming ozone, carbon dioxide, or other compounds depending on atmospheric chemistry. In some cases, they may also escape through interaction with stellar wind particles. Either way, the water molecule that contained them is gone, dissociated into its component elements. This process, called water loss through photolysis, occurs on all planets, with water and ultraviolet exposure. Earth loses water this way, but at rates too slow to matter over geological time. Our planet loses roughly 3 kilograms of hydrogen per second, which sounds like a lot until you calculate how long it would take to drain our oceans at that rate. The answer exceeds the age of the universe many times over. Proxima b, receiving orders of magnitude more ultraviolet radiation, would lose water far more rapidly. The photolysis rate scales with ultraviolet flux. A planet receiving 1,000 times more ultraviolet radiation loses water roughly 1,000 times faster. At the flux levels Proxima b experiences, especially during flares, water loss rates could exceed what Earth experiences by factors of 10,000 or more. Any oceans the planet possessed at formation may have boiled away and been lost to space billions of years ago. The process would have been self-reinforcing. As water vapor accumulated in the atmosphere from heating, it became more exposed to ultraviolet radiation. More exposure meant faster photolysis. Faster photolysis meant faster hydrogen escape. Within hundreds of millions of years, a wet world could transform into a desiccated desert planet. Some scientists have proposed that Proxima b could retain water if its atmosphere contained enough hydrogen. Hydrogen-rich atmospheres absorb ultraviolet radiation in their upper layers, protecting water vapor below. The hydrogen atoms dissociated from hydrogen molecules in the upper atmosphere would need to be replaced by outgassing from the planetary interior. But the water below might survive if the hydrogen shield remained intact. But hydrogen is even lighter than the oxygen atoms that dissociate from water molecules. It escapes even more easily. The stellar wind and coronal mass ejections that strip heavier gases would strip hydrogen with brutal efficiency. Maintaining a hydrogen-rich atmosphere around Proxima b would require continuous outgassing from the planetary interior, replacing hydrogen faster than stellar activity could remove it. This is not impossible in principle. Jupiter's moon Io demonstrates that tidal heating can drive volcanic activity far exceeding anything on Earth. If Proxima b possessed a similar internal heat source, volcanic outgassing might replenish lost hydrogen and other atmospheric gases continuously. But the conditions required for such intense volcanic activity may not exist on Proxima b. And even if they did, the resulting surface environment would pose its own challenges to habitability. The radiation environment also affects potential subsurface habitability, which some researchers have proposed as a refuge for life on otherwise hostile worlds. Earth has deep biospheres, where organisms thrive kilometers below the surface, drawing energy from chemical reactions rather than sunlight. These ecosystems demonstrate that life does not require stellar radiation to persist. They suggest that planets with uninhabitable surfaces might still harbor life in protected underground environments. But red dwarf radiation penetrates deeper than solar radiation on Earth. The X-rays that Proxima Centauri produces during flares can pass through meters of rock before being absorbed. The exact penetration depth depends on rock composition and density, but even buried environments would experience significant radiation exposure during major stellar events. The constant flux of high-energy particles from stellar wind and coronal mass ejections creates secondary radiation as these particles interact with surface materials. Primary cosmic rays strike atomic nuclei in rocks and produce showers of secondary particles that penetrate deeper than the primaries could. Even subsurface environments would experience elevated radiation levels compared to Earth's deep biosphere. Additionally, the energy source for subsurface life remains unclear on Proxima b. On Earth, deep organisms ultimately depend on chemical energy derived from geological processes. Volcanic activity provides reduced chemical compounds like hydrogen sulfide and methane that organisms can oxidize for energy. Radioactive decay of uranium, thorium, and potassium generates heat and drives chemical reactions that produce usable energy compounds. These energy sources require a geologically active planet with internal heat reserves. Earth's internal heat comes from two main sources: residual heat from planetary formation and radioactive decay of long-lived isotopes. This heat drives mantle convection, plate tectonics, and volcanism. The energy flow from Earth's interior to its surface provides the chemical gradients that subsurface organisms exploit. Proxima b's geological activity remains unknown. As a tidally locked world, it experiences reduced tidal heating compared to planets with varying star-planet distances. Tidal heating requires orbital eccentricity, the stretching and compression of a planet as it moves closer to and farther from its star. A perfectly circular orbit produces no tidal heating, regardless of proximity. Proxima b's orbital eccentricity is poorly constrained by current observations. If its orbit is nearly circular, tidal heating may be minimal. If its orbit is significantly eccentric, tidal heating could provide substantial internal energy. But even significant tidal heating may not compensate for the planet's small size, which suggests it may have lost internal heat more rapidly than Earth. Small planets cool faster than large planets because they have larger surface area to volume ratios. Heat escapes through the surface, while heat production occurs throughout the volume. A smaller planet has relatively more surface area compared to its volume, meaning heat escapes more efficiently. Mars, roughly half Earth's diameter, has largely solidified internally. Its volcanic activity appears to have ceased billions of years ago. Proxima B's mass is approximately 1.3 times Earth's mass, suggesting a size somewhat larger than Earth if the compositions are similar, but the composition is unknown. A planet with significant ice or water content could have similar mass to a rocky planet, but different internal structure and thermal evolution. Without knowing the composition, predicting the internal heat budget remains speculative. Without ongoing geological activity, the chemical energy sources that subsurface life requires may simply not exist. The deep biosphere on Earth depends on continuous chemical inputs from geological processes. A geologically dead planet would offer no such inputs. Any subsurface life that evolved when the planet was more active would face energy starvation as geological processes shut down. The cumulative picture of Proxima B's radiation environment should give pause to anyone imagining the planet as a potential human destination. We are not talking about radiation levels that protective equipment might mitigate with sufficient engineering. We are talking about an environment fundamentally incompatible with biological existence as we understand it. Consider the practicalities of human colonization. A human colony on Proxima B would need radiation shielding capable of blocking X-rays and extreme ultraviolet continuously. This shielding would need to consist of dense material, perhaps lead or water, arranged in layers thick enough to absorb the most energetic photons the star produces. The shielding would need to withstand sudden flux increases of thousands of times normal during flares. A structure designed for average radiation levels would become a death trap during major stellar events. The engineering margins would need to anticipate the worst-case scenarios, not the typical conditions. The shielding would need to completely enclose any habitable space because radiation arrives from a fixed position in the sky. With the planet tidally locked, the star never moves from its apparent position. Unlike Earth, where the sun rises and sets, providing half of each day shielded by the planet itself, Proxima B's day side faces constant stellar exposure. Colonists could not simply wait for night to reduce radiation. Night never comes to the day side. The colonists would never see the star directly. Any window or viewport facing the day side would become a death trap during flares. Transparent materials that emit visible light also emit ultraviolet radiation. The warning time between flare onset and lethal radiation exposure might measure in seconds. No human could react quickly enough to seek shelter once a flare began. Outdoor activity would be impossible on the day side under any circumstances. Spacesuit materials that protect against vacuum and temperature extremes would provide minimal protection against the radiation environment. Extravehicular activity would require heavily shielded vehicles rather than personal suits. Even brief exposure during equipment malfunctions could prove fatal. The night side, frozen and dark, would offer no radiation from the star but also no energy input for survival. Temperatures on the night side might approach negative 200 degrees Celsius. Any human presence would require artificial heating and lighting that the colony would need to generate and maintain indefinitely. Some have proposed that the terminator zone might offer protection. If colonists positioned themselves precisely at the boundary between day and night, the star would hang perpetually at the horizon. Perhaps atmospheric scattering would reduce radiation to survivable levels. Perhaps the planet's curvature would provide partial shielding by placing most of the stellar disk below the local horizon. But these proposals ignore the dynamics of the terminator zone. This boundary region is not a stable, calm environment. It is the interface between radically different thermal regimes. Atmospheric models predict fierce winds, dramatic temperature gradients, and constant meteorological instability. The terminator zone might be the only region where temperatures permit liquid water, but it would be an environment of perpetual violence. The star that Proxima b orbits is not merely different from our Sun, it is actively hostile to planetary habitability. Every day brings new radiation assaults. Every year accumulates more atmospheric loss. Every billion years erodes whatever protection the planet might have possessed. Red dwarfs have always represented challenging environments for habitability, but Proxima Centauri is particularly extreme. Among the thousands of red dwarfs within a few dozen light-years of Earth, Proxima Centauri ranks among the most magnetically active. Other red dwarfs of similar mass and age produce flares less frequently and with lower peak intensities. The planet we celebrated as potentially habitable happens to orbit one of the worst-case examples of its stellar type. This reality conflicts with our hopes for Proxima b. We wanted to find a second Earth. We wanted to believe that habitable worlds existed within reach. We wanted cosmic company in our loneliness. What we found instead was a reminder that the universe operates according to physics, not human desires. The red dwarf's wrath continues. Every day, Proxima Centauri unleashes energy that strips away whatever atmosphere remains. Every year, the odds of finding any form of life on Proxima b decrease, as models become more sophisticated and observations more complete. The planet exists within a zone of continuous destruction that makes the concept of habitability almost meaningless, yet we cannot look away. Proxima b remains the closest known exoplanet in a star's habitable zone. Understanding its true nature teaches us about planetary science, stellar physics, and the conditions required for life. Even if Proxima b itself is dead, the knowledge we gain from studying it will guide our search for truly habitable worlds elsewhere. The universe has shown us the closest option. It happens to be a radiation-blasted nightmare orbiting an unstable stellar remnant. This should motivate us to look further, to develop better detection methods, and to maintain realistic expectations about what we might find. The line we must not cross is not merely physical distance. It is the line between hope and evidence, between what we wish and what we know. Proxima Centauri has drawn that line for us in stellar fire. The red dwarf's wrath illuminates both the planet beneath it and the limits of habitability in our cosmic neighborhood. Picture a world where the sun never moves, where one hemisphere bakes under constant stellar illumination while the other freezes in permanent darkness, where the concept of day and night loses all meaning, where temperatures vary by hundreds of degrees over distances a human could walk in an afternoon. This is Proxima b. This is what tidal locking creates. And this is why the line between light and darkness on this world represents both the only hope for habitability and a barrier as deadly as any we could imagine. Every human who has ever lived has experienced the rhythm of day and night. The sun rises in the east, climbs across the sky, and sets in the west. Darkness follows light. Light follows darkness. This cycle has repeated every 24 hours for the entire 4.5 billion year history of our planet. It shaped the evolution of every organism that has ever existed on Earth. It determines when we sleep and when we wake. It governs the opening and closing of flowers, the hunting patterns of predators, the migration routes of birds. The daily cycle is so fundamental to our existence that we struggle to imagine life without it. On Proxima b, that cycle does not exist. The sun hangs motionless in the sky, frozen at whatever position it occupied when gravitational forces finally synchronized the planet's rotation with its orbit. For observers on the day side, the star never sets. For observers on the night side, it never rises. The terminator zone between them exists in perpetual twilight, a world of eternal dusk or eternal dawn depending on your perspective. No sunrise will ever paint those skies with color. No sunset will ever mark the transition to night. Time flows forward, but the celestial markers that humans have used to measure time since prehistory remain eternally fixed. Tidal locking is not a rare phenomenon in our universe. The gravitational forces that create this configuration operate throughout the cosmos. Wherever massive bodies orbit in close proximity, our own moon is tidally locked to Earth, which is why we always see the same lunar face. Generation after generation of humans have gazed up at the same craters, the same dark maria, the same patterns that inspired myths and legends across every culture. The far side of the moon remained a complete mystery until spacecraft orbited behind it in 1959. For all of human history before that moment, half of our nearest celestial neighbour was completely unknown. The physics of tidal locking involves the differential gravitational pull that a large body exerts on a smaller one. The near side of the smaller body, being closer, experiences stronger gravitational attraction than the far side. This difference creates a tidal bulge, an elongation of the smaller body toward and away from the larger one. If the smaller body rotates at a different rate than it orbits, this bulge constantly shifts position, and the gravitational interaction creates a torque that gradually slows the rotation. Over millions or billions of years, this torque extracts rotational energy until the rotation period equals the orbital period. At this point, the tidal bulge no longer shifts position, and the system reaches equilibrium. The same face permanently points toward the larger body. The process is complete. The lock is permanent, unless something disrupts the system. Mercury experiences a partial tidal lock with the Sun, rotating 3 times for every 2 orbits in a complex dance called spin-orbit resonance. This 3:2 ratio developed because Mercury's orbit is significantly elliptical rather than circular. The varying gravitational forces throughout its orbit prevented a complete 1-to-1 lock, while still producing a stable, resonant configuration. Mercury demonstrates that tidal interactions do not always produce simple outcomes. The final configuration depends on orbital parameters, planetary properties, and initial conditions. Pluto and its moon Charon are mutually locked, each showing the same face to the other forever. From Pluto's surface, Charon hangs motionless in the sky, never rising, never setting, never changing position. From Charon's surface, Pluto does the same. This mutual lock developed because the two bodies are relatively similar in mass. Both experience tidal torques that synchronize their rotations with each other. They now rotate and orbit in perfect synchrony, a cosmic waltz frozen in time. But Earth has never experienced a tidally locked relationship with the Sun. Our planet rotates independently, spinning once every 24 hours regardless of our orbital position. This rotation distributes stellar energy across our entire surface in daily cycles. The temperature moderation that makes Earth habitable depends fundamentally on this rotation. Night gives the day side time to cool before temperatures rise to dangerous levels. Day gives the night side time to warm before temperatures plunge to uninhabitable depths. The continuous cycle prevents either hemisphere from reaching the thermal extremes that would make complex life impossible. Earth's rotation also drives our weather patterns. The Coriolis effect, which results from rotation, deflects moving air masses and creates the spiral patterns of cyclones and anticyclones. The trade winds, the jet streams, the monsoons, all depend on Earth's rotation for their characteristic behaviours. A non-rotating Earth would have completely different atmospheric circulation, with simple convection cells carrying hot air from the equator toward the poles and cold air returning along the surface. Proxima b has no such protection. Locked in gravitational embrace with its parent star, the planet presents one face to Proxima Centauri permanently. The timescale for this locking was short by astronomical standards. A planet at Proxima b's orbital distance, just 7.5 million kilometers from its star, would typically lock within a few hundred million years after formation. Given that the Proxima Centauri system is 4 to 7 billion years old, Proxima b has almost certainly been tidally locked for most of its existence. The substellar point, the location where the star appears directly overhead, receives constant illumination that never varies except during stellar flares. This single point on the planetary surface absorbs more stellar energy per unit area than any other location. The energy input never stops. Day after day, year after year, billion years after billion years, the same patch of ground bakes under unrelenting stellar radiation. Move away from this point in any direction, and the star drops lower in the sky. The angle of illumination becomes more oblique, spreading the same stellar energy across larger surface areas. The energy received per unit area decreases according to the cosine of the angle from vertical. At 45 degrees from the substellar point, each square meter receives only 70% of the energy that a square meter at the substellar point receives. At 60 degrees, it drops to 50%. At the terminator, where the star sits at the horizon, the illumination becomes theoretically zero, though atmospheric scattering might provide some residual light. Continue beyond the terminator and the star vanishes below the horizon forever. No amount of waiting will bring it back. No season will shift the illumination pattern. The night side of Proxima b has not seen starlight from Proxima Centauri since the planet locked into its current configuration billions of years ago. Whatever warmth that hemisphere possessed at formation radiated away into space long ago. What remains is a frozen wasteland, colder than anything humans have ever experienced. The thermal consequences of this configuration are extreme beyond anything in human experience. Models of tidally locked planets predict dayside temperatures capable of melting lead and nightside temperatures approaching absolute zero. The exact values depend on atmospheric composition and density, but the general pattern remains consistent regardless of assumptions. One side roasts, one side freezes, and the boundary between them becomes the most dynamic environment on the planet. Let us walk across Proxima b's surface and observe what physics predicts we would encounter. This journey exists only in imagination, because no human technology could survive what we are about to describe, but understanding the conditions requires visualizing them as concretely as possible. Start at the substellar point. Here, Proxima Centauri hangs directly overhead, a dim red presence roughly 2.5 times larger in angular diameter than our Sun appears from Earth. The star appears larger because Proxima b orbits so much closer to its star than Earth orbits to the Sun. But despite its apparent size, the star provides less total illumination than Earth receives. Proxima Centauri's cool surface temperature means it emits far less energy per unit area than our Sun. The larger apparent size partially compensates but does not fully offset the lower surface brightness. The light carries a distinctly reddish cast, making colours appear strange to human eyes adapted to solar illumination. Our Sun emits most strongly in the green portion of the visible spectrum, with substantial output across all visible wavelengths. This produces the white light we perceive as normal daylight. Proxima Centauri emits most strongly in the infrared, with its visible output weighted heavily toward red wavelengths. A human observer would perceive an environment bathed in deep crimson light, where blues and greens appear muted and reds appear oversaturated. Surface temperatures at the substellar point depend critically on atmospheric properties. The calculation involves balancing energy input from the star against energy output through thermal radiation. A bare rock surface with no atmosphere would reach equilibrium when its thermal emissions equal its stellar absorption. For Proxima b's orbital distance and Proxima Centauri's luminosity, this equilibrium temperature could reach 500 degrees Celsius or higher. If Proxima b possesses a thick atmosphere, convection and winds would distribute heat away from the substellar point toward cooler regions. The atmosphere acts as a thermal buffer, preventing the extreme temperatures that a bare surface would experience. Carbon dioxide atmospheres are particularly effective at this heat distribution because carbon dioxide is a strong infrared absorber. A thick carbon dioxide atmosphere could potentially maintain surface temperatures within the range where liquid water exists. But even optimistic models predict substellar temperatures exceeding the boiling point of water at standard pressure. The energy input at the substellar point is simply too intense for liquid water to persist on exposed surfaces. Any water present would vaporize immediately, adding steam to the atmosphere. This steam would absorb additional stellar radiation in the infrared, potentially creating a runaway feedback that pushes temperatures even higher. The runaway greenhouse effect that Venus experienced demonstrates how this feedback can spiral out of control. Venus likely possessed surface water early in its history, but solar heating vaporized this water into the atmosphere. Water vapor is a powerful greenhouse gas. The additional water vapor trapped more heat, which vaporized more water, which trapped more heat. The feedback continued until the oceans were entirely vaporized, and the surface temperature reached its current level of over 460 degrees Celsius. Proxima b could have experienced a similar runaway on its day side, even if conditions on the night side or terminator permitted cooler temperatures. The substellar region might have lost any water it possessed billions of years ago through this same feedback mechanism. The stone beneath the eternal red sun might have been dry and barren for longer than Earth has existed. Walk away from the substellar point in any direction. With each step, Proxima Centauri drops lower in the sky. The stellar illumination angle becomes more oblique, spreading the same energy across larger surface areas. Temperatures decrease accordingly. The gradient is steep by Earth standards. Walking 100 kilometers from the substellar point might reduce temperatures by 50 degrees or more depending on atmospheric properties. At roughly 45 degrees from the substellar point, measured along the planetary surface, temperatures might drop to levels where liquid water could theoretically exist. This ring around the substellar point, at constant angular distance from the star's overhead position, represents a first candidate zone for habitability. If atmospheric heat transport is efficient, if the surface pressure is appropriate, if water is present, then liquid might persist in this annular region. But this zone faces constant challenges from the stellar environment. The radiation that Part 2 described falls on this region, as well as on the substellar point. Ultraviolet and X-ray flux would damage any biological molecules attempting to function in exposed water bodies. Stellar flares would periodically sterilize the surface. Whatever water exists would need to be shielded from radiation, either by atmosphere or by rock. Continue walking. The star drops toward the horizon. The landscape grows darker and colder with each step. Temperatures that might have permitted water become temperatures that freeze it. The transition occurs over distances that would be trivial by Earth standards. A few hundred kilometers might span the entire range from boiling to freezing depending on atmospheric conditions. The twilight deepens. Shadows lengthen toward infinity because the sun never moves. On Earth, shadows shift throughout the day as the sun crosses the sky. The direction and length of shadows provide information about time. On Proxima b, shadows point in the same direction forever. They neither lengthen nor shorten. They neither rotate nor shift. Time passes, but the shadows do not know it. You are approaching the terminator zone. The terminator zone runs completely around Proxima b like a great circle dividing the planet into hemispheres. This line marks the boundary where the star sits perpetually at the horizon. Half the sky glows with dim red light from the star and its atmospheric scattering. The other half remains dark, sprinkled with stars that never set and never rise. This is the boundary between two worlds, the interface where eternal day meets eternal night, the only region where temperatures might permit liquid water without either the extreme heat of the substellar region or the extreme cold of the antistellar region. The geometry of the terminator zone deserves careful consideration. On a perfectly spherical planet with no atmosphere, the terminator would be a mathematical line of zero width. It would mark the exact points where stellar rays arrive tangent to the surface, neither illuminating nor shadowing. In reality, planets are not perfect spheres, and atmospheres scatter light beyond the geometric terminator. Atmospheric refraction bends starlight around the curve of the planet, extending illumination into what would geometrically be the night side. On Earth, this effect adds several minutes to the length of day at sunrise and sunset. The sun remains visible after it has geometrically set below the horizon, because Earth's atmosphere bends the light path. On Proxima b, similar refraction would widen the terminator zone, creating a broader region of twilight illumination. But the terminator zone is not a gentle place. It represents the front line of a thermal war between burning day and frozen night. The temperature gradient across this zone measures tens of degrees per kilometer in extreme models. Walking toward the day side raises temperatures rapidly. Walking toward the night side drops them just as fast. Any liquid water in the terminator zone would exist in an extremely narrow band, perhaps only tens of kilometers wide on a planetary scale. Consider what this narrowness means for any hypothetical life. On Earth, organisms can migrate across thousands of kilometers to find suitable temperatures. Birds fly from Arctic breeding grounds to tropical wintering sites. Whales travel from polar feeding waters to equatorial breeding lagoons. This mobility allows organisms to exploit resources across vast distances and survive environmental variations. On Proxima B's terminator zone, the habitable band might be narrower than many organisms' daily movement ranges. A creature that walked 10 kilometers in the wrong direction could experience a temperature change of hundreds of degrees. Migration as a survival strategy becomes almost meaningless when the entire habitable range spans less than a day's journey. Any organisms would need to maintain precise positional awareness, staying within the narrow band where temperatures permit survival. This narrowness creates problems for atmospheric dynamics that dominate conditions in the terminator zone. Air over the hot day side expands as heating increases the kinetic energy of gas molecules. Expanded air is less dense than cold air at the same pressure, so it rises through buoyancy. This creates a low-pressure region at the surface as air flows away at altitude. Air over the cold night side experiences the opposite process. Cooling reduces the kinetic energy of gas molecules, causing the atmosphere to contract. Contracted air is denser, so it sinks toward the surface. This creates a high-pressure region as air accumulates faster than it can flow away. The pressure difference between the hot day side and the cold night side drives atmospheric circulation. At altitude, the circulation reverses, with air flowing from the day side toward the night side to replace the air that sank. But this circulation does not occur smoothly across the entire planetary surface. The transition happens abruptly at the terminator zone, where temperatures change rapidly over short distances. The terminator becomes a region of extreme wind shear and turbulence as air masses at dramatically different temperatures collide and mix. Atmospheric models of tidally locked planets predict persistent hurricane-force winds along the terminator. The pressure gradient between hemispheres must equalize somehow, and the terminator zone becomes the pressure release valve. Winds exceeding 300 kilometers per hour might blow continuously along this boundary, never stopping, never calming. A permanent storm system circling the planet. The transition zone becomes a planet-girdling vortex where temperature extremes collide. Hot air rushing toward the day side at altitude meets cold air rushing toward the night side at the surface. The mixing creates massive convective cells, vertical circulation patterns that transport heat and material between different atmospheric layers. Thunderstorms might be permanent features, with lightning discharging continuously as charged particles separate in the turbulent flow. Any surface features in this region would experience constant erosion from winds carrying dust and debris from both hemispheres. Mountains would weather faster than on any Earth environment. Valleys would fill with wind-deposited material. The landscape would be shaped not by water or ice, but by the relentless atmospheric currents that flow eternally along the terminator. Some models suggest the atmospheric dynamics might be even more violent. If the night side becomes cold enough, atmospheric gases themselves could condense and freeze out. Nitrogen freezes at negative 210 degrees Celsius at standard pressure. Oxygen freezes at negative 219 degrees. If night side temperatures drop below these thresholds, the atmosphere itself would begin falling as snow. Nitrogen and oxygen crystals would precipitate from the sky, accumulating as frozen deposits in the permanent darkness. This atmospheric collapse would reduce pressure on the night side dramatically. Where a full atmosphere once existed, near vacuum conditions might develop as most of the gas transfers to the solid phase. The pressure difference between the day side, with its hot, expanded atmosphere, and the night side, with its collapsed, frozen atmosphere, could become extreme. Pressure gradients of this magnitude would drive winds approaching the speed of sound. These supersonic jets would flow from day to night continuously, carrying heat and gas in a one-way transfer. The supersonic winds might eventually strip atmosphere from the day side as well. Gas molecules accelerated to high velocities in the terminator flow might exceed escape velocity, bleeding into space rather than reaching the night side. The planet could lose its atmosphere gradually through this process, with the terminator zone serving as the escape route. Whether Proxima b experiences atmospheric collapse depends on factors we cannot currently observe. The presence of greenhouse gases could keep the night side warm enough to prevent collapse. Carbon dioxide remains gaseous down to much lower temperatures than nitrogen or oxygen. A carbon dioxide-dominated atmosphere might maintain gas phase throughout the night side, even at very low temperatures. A thick initial atmosphere might resist collapse through sheer thermal mass. More atmosphere means more heat capacity, which slows the cooling rate. If the atmosphere is thick enough, heat transport from the day side might keep the night side above condensation temperatures, even with minimal direct stellar input. Ongoing volcanic outgassing could replenish lost atmosphere continuously. If Proxima b possesses geological activity, volcanoes might release gases faster than atmospheric collapse can remove them. The atmosphere would reach a steady state where loss and replenishment balance. But these are hopeful assumptions, not observed facts. We have no direct evidence about Proxima b's atmospheric composition, thickness, or stability. The models that predict atmospheric collapse and those that predict stability make different assumptions about unknown parameters. Until we can observe the planet directly, we cannot know which scenario applies. Continue walking into the night side. The terminator zone falls behind you. Proxima Centauri drops below the horizon forever. The dim red glow of the star fades into complete darkness. The sky reveals itself in ways impossible on Earth, where atmospheric scattering and light pollution obscure our view of the cosmos. The sky darkens to reveal stars that do not twinkle. Twinkling results from atmospheric turbulence, refracting starlight through varying density layers. If Proxima b's night side has lost its atmosphere to freezing, the stars would shine with steady, unwavering light. Every point of light would appear perfectly sharp, without the scintillation that makes stars seem alive from Earth's surface. Or perhaps there is an atmosphere, but it is frozen solid, deposited as nitrogen and oxygen ice across the landscape. The ice would be transparent in thin layers, but might appear bluish or whitish in accumulation. Drifts of frozen atmosphere would cover the terrain, filling valleys and burying features. The landscape would resemble nothing on Earth, a world where the very air has become solid. Surface temperatures on the night side approach the cosmic background level of -270 degrees Celsius. This temperature represents the equilibrium point where an object in deep space radiates exactly as much heat as it absorbs from the cosmic microwave background radiation. No natural process can cool an object below this temperature, because the radiation from the background provides a constant heat input. At these temperatures, most chemical reactions cease entirely. Chemical reactions require molecular motion to bring reactants into contact. At -270 degrees, molecules have almost no kinetic energy. They sit frozen in place, unable to react with their neighbours regardless of chemical affinity. Life as we know it depends on chemistry. On Proxima b's night side, chemistry essentially stops. Any water present froze billions of years ago, when the planet first locked into its current configuration. The ice would be ancient beyond comprehension, undisturbed since before complex life evolved on Earth. Any organic molecules present either froze as well, or were destroyed by radiation penetrating from the day side over geological time. The night side of Proxima b represents one of the coldest environments accessible to human exploration within our stellar neighborhood. Even the surface of Pluto, at -230 degrees Celsius, seems balmy by comparison. Pluto receives some solar illumination, however dim, that prevents temperatures from dropping to the cosmic background level. Proxima B's night side receives no stellar input whatsoever. The eternal darkness creates conditions that would challenge any survival technology we possess. Metals become brittle at these temperatures. Lubricants freeze solid. Electronic components fail as semiconductors lose their properties. Even the power sources that might operate in extreme cold, like radioisotope thermoelectric generators, would face challenges dissipating waste heat in an environment this cold. But the night side might offer one advantage that no other region of Proxima b provides. It provides complete shielding from Proxima Centauri's radiation. The planet itself blocks all electromagnetic radiation from the star. X-rays cannot penetrate thousands of kilometers of rock. Ultraviolet cannot curve around a spherical planet. Any colonists seeking protection from stellar flares could position themselves on the night side, using the planet itself as a radiation shield. They would need artificial lighting, heating, and life support. But they would not face the constant bombardment that makes the day side uninhabitable. The night side trades one set of extreme challenges for another. Instead of radiation and heat, visitors would face darkness and cold. Both extremes would require technological solutions, but the night side's challenges are at least familiar from Earth experience. We know how to provide light and heat. We know less about how to shield against intense X-ray flares. This possibility has led some scientists to suggest that any life on Proxima b would have migrated to subsurface environments on the night side. Here, warmed by geothermal heat from the planetary interior, shielded from radiation by kilometers of rock and ice, organisms might find a refuge from the hostile surface environment. The energy budget would be challenging. Life requires energy to power metabolism, growth, and reproduction. On Earth's surface, most energy comes ultimately from sunlight through photosynthesis. On Proxima b's night side, no sunlight exists. Organisms would need alternative energy sources, probably geothermal heat driving chemical reactions that release usable energy. Earth has examples of such ecosystems. Deep-sea hydrothermal vents support complex communities far from any sunlight. These organisms derive energy from chemical reactions between hot, mineral-rich vent fluid and cold seawater. Bacteria oxidize hydrogen sulfide and other reduced compounds, forming the base of a food web that includes tube worms, crabs, and fish. Subsurface environments on Proxima b might support similar ecosystems if the planet possesses geological activity. Hot springs or hydrothermal vents could provide both warmth and chemical energy. Organisms might cluster around these energy sources, evolving specialized biochemistry to exploit whatever chemical gradients exist. The problem is finding such life. Subsurface environments on the night side of a planet 4 light-years away remain beyond any detection method we possess. We cannot image the surface of Proxima b with current telescopes. We certainly cannot probe beneath that surface. We cannot even confirm whether the planet has geological activity, liquid water, or any of the other prerequisites for subsurface habitability. The possibility remains speculative, interesting to consider, but impossible to verify with current technology. Return now to the Terminator zone, that thin band of twilight where temperatures might permit liquid water. This region has attracted the most scientific attention as a potential habitable niche because it is the only region where conditions at the surface might fall within the range where Earth-like life could function. The Terminator zone on a planet like Proxima b would span roughly 5% of the planetary surface. A band, perhaps 1,000 kilometers wide, circling a world approximately 12,000 kilometers in circumference. This represents an area similar to the Sahara Desert, roughly 9 million square kilometers. Not vast by planetary standards, but not trivial either. More than enough space for ecosystems to develop if other conditions cooperate. Within this zone, microclimates might develop based on local topography and surface properties. Mountainous regions could create rain shadows and temperature variations. A mountain range running perpendicular to the terminator might block atmospheric flow, creating distinct climate zones on each side. Low-lying areas might collect water and maintain higher humidity, potentially supporting more complex ecosystems. The constant star at the horizon would create perpetual long shadows, with some surfaces illuminated and others permanently dark. The shadowed areas might provide refuge from radiation while maintaining temperatures above freezing. Complex terrain could create thousands of microhabitats with slightly different conditions, providing opportunities for evolutionary diversification. Plants adapted to such an environment would need to cope with dim, reddish light arriving at extreme angles. Photosynthesis as we know it requires specific wavelengths that Proxima Centauri provides in limited quantity. Earth plants use chlorophyll that absorbs red and blue light most efficiently, reflecting green light to give leaves their characteristic color. The limited blue light from Proxima Centauri would make chlorophyll-based photosynthesis inefficient. Any photosynthetic life on Proxima b would need different pigments, different energy strategies, and different growth patterns than Earth organisms. They might evolve pigments that absorb across the infrared spectrum, where Proxima Centauri emits most strongly. They might appear black to human eyes, absorbing all visible wavelengths rather than reflecting green. Their growth patterns would orient toward the eternally fixed star position rather than tracking a moving sun across the sky. Animals in the terminator zone would face constant decisions about temperature regulation. Moving toward the day side would provide warmth but risk overheating and radiation exposure. Moving toward the night side would provide coolness and radiation protection but risk freezing. Any complex organisms would need behavioral strategies for navigating this thermal gradient, perhaps following daily activity patterns dictated by stellar flare forecasts rather than sunrise and sunset. But these speculations assume the terminator zone remains stable over evolutionary timescales. In reality, several factors could shift the zone's position or eliminate it entirely, disrupting any ecosystems that had developed. Atmospheric changes represent the primary threat. If greenhouse gas concentrations increase through volcanic outgassing or other processes, the planet warms overall. The terminator zone would shift toward the night side as temperatures that once required direct stellar illumination become achievable through greenhouse warming alone. Any organisms adapted to the original terminator position would find their habitat disappearing beneath them. If atmospheric gases freeze out or escape to space, the planet cools and the terminator zone shifts toward the day side. The region that once supported liquid water would freeze as heat transport from the day side decreases. Again, any organisms would need to migrate to follow the shifting habitable zone. Stellar activity provides another mechanism for change. Major flares heat the day-side atmosphere, causing it to expand toward the night side. The temporary heating might shift the terminator zone significantly, potentially displacing it by hundreds of kilometers during major events. Organisms that cannot move fast enough would find themselves suddenly exposed to lethal temperatures. Coronal mass ejections strip atmospheric gases, reducing the atmospheric mass available to distribute heat. Over billions of years, these events accumulate, gradually thinning the atmosphere and shifting the thermal balance. The terminator zone might have occupied a different position a billion years ago than it occupies today. It might occupy a different position a billion years from now. Orbital variations might also play a role in terminator zone stability. Proxima b does not orbit in perfect circular fashion. Its orbit has some eccentricity, meaning the planet-star distance varies throughout the 11-day year. At closest approach, the star appears larger and delivers more radiation. At farthest distance, the star appears smaller and delivers less. This variation could cause the terminator zone to oscillate back and forth, expanding and contracting with the orbital period. The accumulated uncertainties make detailed predictions about the terminator zone's habitability impossible. We can describe general physical processes. We can model atmospheric dynamics. We can calculate temperature distributions. But we cannot observe the actual conditions on Proxima B's surface directly. Every statement about surface habitability is a prediction based on models that may or may not capture the relevant physics accurately. What we can say with confidence is that tidal locking creates an environment radically different from anything on Earth. The constant day side and constant night side divide the planet into two worlds with almost nothing in common. The terminator zone connecting them represents an extreme environment by any standard. A boundary where physical parameters change more rapidly with distance than any location on our home planet. This is the line that gives our story its title. The boundary between light and darkness on Proxima B, the strip of perpetual twilight where temperatures might permit liquid water, the only candidate for habitability on our nearest exoplanet neighbour. The line, you must not cross, but calling this line a potential habitable zone misrepresents the reality. The terminator zone is a battlefront, a collision between thermal extremes, a place of constant atmospheric violence where any liquid water would face freezing, boiling, or both, depending on local conditions and recent stellar activity. The line you must not cross is literal on Proxima B. Cross it in one direction, and you face temperatures that would cook you alive within hours or minutes. Cross it in the other direction, and you face temperatures that would freeze you solid in seconds. Remain on the line, and you face winds that would tear you apart, temperatures that fluctuate with every stellar flare, and radiation that penetrates any shelter you might construct. There is no safe direction on this world. There is no refuge from the physical extremes that tidal locking creates. The terminator zone offers the best conditions available, and those conditions would kill any unprotected human faster than the most hostile environments on Earth. Our nearest potentially habitable exoplanet is not merely challenging, it is a world designed by physics to prevent habitability. Every aspect of its configuration works against the development and maintenance of life. The red dwarf that warms it also sterilizes it. The proximity that keeps it warm, the eternal twilight that might permit water also creates atmospheric chaos. Yet we continue studying Proxima B. We continue modeling its atmosphere and speculating about its surface. We continue hoping that somewhere, somehow, conditions might allow life to persist. This hope says more about human psychology than about Proxima B's actual habitability. The universe does not owe us neighbours. It does not owe us company in our cosmic loneliness. Proxima B exists not as a potential home, but as a lesson, a demonstration of what habitable zone really means and how far that concept falls short of actually habitable. The terminator zone remains the best candidate for life on Proxima B. It also remains an environment that would kill any Earth organism in seconds of unprotected exposure. This is the line we must not cross. Not because crossing it is technically difficult, but because crossing it would be instantly fatal. 4.24 light-years. The distance separating Earth from Proxima B, a number that sounds manageable until you try to comprehend what it actually means. Light itself, moving at the absolute speed limit of the universe, requires more than 4 years to cross this gap. The fastest spacecraft humanity has ever built would need tens of thousands of years. The cosmic abyss between our world and our nearest exoplanet neighbour represents a barrier so profound that it may forever remain uncrossable. When astronomers announced the discovery of Proxima B in 2016, the proximity seemed like a gift. 4 light-years, practically next door by cosmic standards. The nearest star system to our own happened to contain a rocky planet in its habitable zone. What incredible luck. What perfect timing. Surely this meant that reaching another potentially habitable world lay within humanity's grasp. This optimism fundamentally misunderstood what 4 light-years actually means. The number sounds small because we are accustomed to thinking about cosmic distances in terms of billions of light-years to distant galaxies. Compared to the edge of the observable universe at 46 billion light-years, 4 light-years seems trivial. But this comparison deceives us. The relevant comparison is not to the edge of the universe, but to the distances human technology can actually traverse. Let us begin with the mathematics of interstellar distance, because only through mathematics can we truly appreciate the barrier that separates us from Proxima b. 1 light-year equals the distance that light travels in 1 year. Light moves at approximately 300,000 kilometers per second, the fastest speed possible in our universe, according to Einstein's special relativity. Nothing that carries information or mass can exceed this velocity. It represents an absolute limit built into the fabric of space-time itself. In 1 second, light travels far enough to circle Earth 7.5 times. In 1 minute, light travels 18 million kilometers, roughly halfway to Venus at its closest approach. In 1 hour, light travels over 1 billion kilometers, nearly the distance from the Sun to Saturn. In 1 day, light travels 26 billion kilometers, well past the orbit of Neptune. In 1 year, light travels 9.46 trillion kilometers. Multiply this by 4.24, and you get approximately 40 trillion kilometers between Earth and Proxima b. Written out in full, this number is 40,000 billion kilometers. It contains 13 digits. The human mind cannot visualize such distances. We can only process them as abstract numbers stripped of any connection to lived experience. Consider some comparisons that might make this distance more tangible, though even these comparisons ultimately fail to convey the true scale. The distance from Earth to the Moon, which astronauts crossed in 3 days during the Apollo missions, measures approximately 384,000 kilometers. The distance to Proxima b equals 104 million trips to the Moon. If you lined up that many Moon missions end to end, the chain would stretch from here to our nearest stellar neighbor. The distance from Earth to the Sun, 1 astronomical unit, measures 150 million kilometers. This is the yardstick astronomers use for measuring our solar system. Proxima b lies 268,000 astronomical units away. If you could somehow travel from Earth to the Sun in 1 hour, which would require moving at 42,000 kilometers per second, the journey to Proxima b would still take 30 years. If you could drive a car at highway speeds toward Proxima Centauri, maintaining 100 kilometers per hour continuously, without stopping for fuel, rest, or mechanical failure, the journey would require 48 million years. The dinosaurs went extinct 66 million years ago. You would arrive before they died if you measured backward through geological time. The entire history of complex life on Earth would pass during your journey. Walking at a brisk 5 kilometers per hour, the trip would require 900 million years. When you arrived, the sun would have brightened enough to begin boiling Earth's oceans. You would reach your destination only to learn that your home world had become uninhabitable during your absence. These comparisons illustrate why interstellar distances represent a fundamentally different challenge than anything humans have previously attempted. We are not talking about scaling up existing technology by factors of 10 or 100. We are talking about challenges that exceed current capabilities by factors of millions or billions. Voyager 1, launched in 1977, represents the fastest object humanity has ever sent toward the stars. After using gravity assist from Jupiter and Saturn, Voyager achieved a velocity of approximately 17 kilometers per second relative to the Sun. This is roughly 61,000 kilometers per hour, fast enough to circle Earth in 40 minutes. By human standards, Voyager moves with incredible speed. By interstellar standards, Voyager crawls. At 17 kilometers per second, Voyager 1 would require approximately 73,000 years to reach Proxima Centauri if it were heading in that direction. It is not. Voyager travels toward a different region of space, carrying its golden record of human sounds and images into an interstellar void that will swallow it long before it approaches any star. In about 40,000 years, Voyager will pass within 1.6 light-years of the star Gliese 445, but it will not come close enough to any star's planetary system for meaningful observation. The New Horizons spacecraft, which reached Pluto in 2015 after a 9-year journey, travels at roughly 16 kilometers per second. At this speed, the journey to Proxima b would exceed 80,000 years. 80,000 years ago, Homo sapiens had not yet migrated out of Africa in significant numbers. Neanderthals still inhabited Europe. The entire span of human civilization, from the first agricultural settlements to the present day, represents less than 15% of the time New Horizons would need to reach our nearest stellar neighbour. These numbers illustrate the fundamental problem of interstellar travel. The universe is simply too big. The distances between stars dwarf any scale human technology can reasonably address. Even proposals that push the absolute limits of known physics require time frames exceeding human lifetimes, human civilizations, and possibly human species duration. The speed of light itself conspires against us. If we could somehow accelerate a spacecraft to 90% of light speed, the journey to Proxima b would still require nearly 5 years from the perspective of observers on Earth. The travelers themselves, experiencing time dilation effects predicted by special relativity, might perceive the journey as lasting only about 2 years. But achieving 90% of light speed requires energy input so enormous that they exceed the total energy consumption of human civilization throughout all of history. The energy required to accelerate mass increases without limit as velocity approaches light speed. This is not an engineering limitation that clever design might overcome. It is a fundamental feature of space-time geometry. The faster an object moves, the more energy is required to accelerate it further. At 99% of light speed, a 1 kilogram object has kinetic energy equivalent to about 20 megatons of TNT. At 99.9%, the energy increases by another factor of 3. The asymptotic approach to light speed demands infinite energy for any object with mass. But let us examine what it would actually take to reach Proxima b within human-relevant timescales, setting aside for the moment whether the destination would be worth reaching. The most aggressive interstellar travel concepts currently under serious consideration propose light sails accelerated by powerful ground-based or space-based lasers. The Breakthrough Starshot initiative, announced in 2016 with funding from Russian billionaire Yuri Milner, aims to send gram-scale spacecraft to Proxima Centauri at 20% the speed of light. At this velocity, approximately 60,000 kilometers per second, the journey would require approximately 20 years. Add 4.2 years for any data to return to Earth at light speed, and scientists would receive information about Proxima b within a single human career. 20% light speed sounds achievable compared to the impossibility of faster-than-light travel. The physics works. Special relativity permits objects to travel at any speed below light speed given sufficient energy input. 20% represents a target that does not run into fundamental physical barriers, merely engineering challenges of unprecedented scale. But those engineering challenges are staggering. Accelerating even a 1-gram spacecraft to 60,000 kilometers per second requires enormous energy input. The kinetic energy of a 1-gram object at 20% light speed equals approximately 1.8 trillion joules. This is equivalent to about 430 tons of TNT, roughly the yield of a small tactical nuclear weapon for a single gram of matter. A paperclip weighs about 1 gram. The Breakthrough Starshot concept envisions delivering this energy through a powerful laser beam that pushes on a reflective sail attached to the spacecraft. The sail would unfurl to perhaps 4 meters on a side, presenting 16 square meters of reflective surface to the laser beam. As photons bounce off the sail, they transfer momentum to the spacecraft, accelerating it gradually. The concept envisions a 100-gigawatt laser array firing for approximately 10 minutes to accelerate the tiny probe to 20% light speed. For comparison, the entire electrical generation capacity of the United States totals roughly 1,000 gigawatts, distributed across thousands of power plants. Breakthrough Starshot would require concentrating 10% of American generating capacity into a single laser beam for 10 minutes. The energy consumed during this 10-minute firing would equal roughly 600 billion joules, equivalent to the annual electricity consumption of millions of households. Every launch would require this energy investment, and the concept envisions launching hundreds or thousands of probes to ensure that at least some survive the journey and return data. The laser array itself would need to span kilometers to maintain beam coherence over the acceleration distance. Light naturally spreads as it travels, a phenomenon called diffraction. A laser beam aimed at a target millions of kilometers away would spread to cover an area larger than the tiny sail unless the beam originates from an aperture many kilometers across. This could be achieved through an array of smaller lasers operating in precise synchronization, but building and operating such an array presents engineering challenges that no one has yet solved. The array would need to track the accelerating spacecraft with extreme precision as it recedes from Earth at increasing velocity. Any slight misalignment would cause the beam to miss the sail, wasting energy and potentially destroying the spacecraft through uneven heating. The tracking system would need to maintain accuracy measured in fractions of an arc-second over distances measured in millions of kilometers. Construction would require advances in laser technology, adaptive optics, power distribution, and space-based infrastructure that remain decades away under even optimistic projections. The total cost likely exceeds $100 billion, approaching the scale of entire national space programs. The International Space Station cost approximately $150 billion over its lifetime. Breakthrough Starshot proposes a comparable investment for a mission that would return a few photographs and some spectroscopic data. And what would this $100 billion buy? A spacecraft weighing less than a paperclip, equipped with a camera and a communication system, capable of flying past Proxima b at 60,000 kilometers per second. The flyby would last minutes at most. At that velocity, the spacecraft would cross a distance equal to Earth's diameter in about 1/5 of a second. Any images would be blurred by the extreme relative motion unless sophisticated stabilization systems compensated perfectly. The probe could not slow down, enter orbit, or land. Deceleration would require carrying fuel or deploying another sail to catch a laser beam fired from the destination, neither of which is feasible for a gram-scale spacecraft. The probe would simply streak through the Proxima Centauri system and continue into interstellar space, eventually becoming yet another piece of debris drifting through the galaxy. We would get one chance to gather data during the brief encounter, and then the spacecraft would be gone forever. The data returned from such a mission would be valuable but limited. We might confirm whether Proxima b possesses an atmosphere by observing how starlight filters through its limb during the approach. We might image its surface at resolution surpassing Earth-based telescopes, though the resolution would still be limited by the small aperture of a gram-scale camera. We might detect signatures of chemical compounds through spectroscopy, compounds that might suggest geological or biological activity, but we would not explore the planet. We would not search systematically for life. We would not land instruments on the surface to measure conditions directly. We would glimpse Proxima b for seconds and then lose contact forever as the probe continued its journey into the interstellar void. Sending a spacecraft capable of slowing down and entering orbit multiplies the difficulty by orders of magnitude. Deceleration requires carrying fuel, which increases mass, which requires more fuel to accelerate in the first place. This vicious cycle is called the tyranny of the rocket equation, and it makes high-speed missions with substantial payloads essentially impossible using any propulsion technology humans currently possess. The rocket equation states that the final velocity a rocket can achieve depends logarithmically on the ratio of initial mass to final mass. To double your final velocity, you need to square your mass ratio, not merely double it. For the extreme velocities required for interstellar travel, the mass ratios become absurd. A spacecraft that needs to accelerate to 20% light speed and then decelerate to orbit would need to carry fuel that outweighs the payload by factors of millions or billions. Chemical rockets, the technology that carried humans to the moon, produce exhaust velocities of a few kilometers per second. Achieving interstellar velocities with chemical rockets would require mass ratios exceeding the number of atoms in the observable universe. Ion engines, which use electrical energy to accelerate propellant to higher velocities, improve the situation, but not enough. Even the most efficient ion engines produce exhaust velocities of only a few tens of kilometers per second, still far too slow for practical interstellar propulsion. Nuclear pulse propulsion, proposed in the 1950s Project Orion concept, could theoretically accelerate large spacecraft to several percent of light speed. This approach uses sequential nuclear explosions behind a massive pusher plate to generate thrust. A series of atomic bombs would detonate at regular intervals, each blast pushing the spacecraft faster through the recoil of ablated plate material and bomb debris. The physics is sound. Nuclear explosions release enormous energy from relatively small masses. A series of thousands of nuclear detonations could theoretically accelerate a 1,000-ton spacecraft to perhaps 5% of light speed. At this velocity, the journey to Proxima b would require roughly 85 years. A human launched at birth might survive to see arrival if significant life extension technology were developed during the voyage. More practically, such a mission would span multiple human generations. Those who launched would not arrive. Those who arrived would not remember Earth. The engineering challenges of nuclear pulse propulsion are substantial, but not obviously insurmountable. The pusher plate would need to survive thousands of nuclear explosions, each delivering a massive shock. The spacecraft would need to carry thousands of nuclear devices and deploy them with precise timing. The crew would need protection from the intense radiation environment created by continuous nuclear detonation, but the political and practical obstacles may prove insurmountable regardless of engineering feasibility. The Partial Nuclear Test Ban Treaty of 1963 prohibits nuclear weapon tests in space. Launching thousands of nuclear devices raises obvious safety and proliferation concerns. A launch accident that scattered nuclear weapons across the Atlantic would represent an unprecedented disaster. The technology, while theoretically sound, remains firmly in the realm of speculation because no political consensus exists to pursue it. Antimatter propulsion offers even higher theoretical performance than nuclear pulse systems. When matter and antimatter meet, they annihilate completely, converting 100% of their combined mass into energy. This is the most efficient energy release known to physics, far exceeding nuclear fission at roughly 0.1% efficiency or nuclear fusion at roughly 0.7% efficiency. A gram of antimatter annihilating with a gram of ordinary matter releases energy equivalent to about 43 kilotons of TNT, roughly 3 times the yield of the Hiroshima bomb. Properly harnessed, antimatter could theoretically accelerate spacecraft to significant fractions of light speed. A spacecraft carrying 10 kilograms of antimatter and 10 kilograms of reaction mass could theoretically achieve velocities approaching 50% of light speed. The problem is producing antimatter. Creating antimatter requires particle accelerators that consume enormous energy to generate tiny quantities of antiparticles. Current facilities like CERN produce antimatter in quantities measured in nanograms per year. Producing the kilograms of antimatter needed for interstellar propulsion would require scaling up production by factors of trillions while simultaneously reducing costs by similar factors. The energy cost of antimatter production exceeds the energy released in annihilation by factors of billions with current technology. We invest vastly more energy creating antimatter than we could ever recover by annihilating it. This means antimatter functions as an extremely inefficient energy storage medium rather than an energy source. We would need to invest colossal energy to create the antimatter, store it safely without allowing it to contact normal matter, and then release that energy during the mission. Even if production efficiency improved dramatically, storage presents another challenge. Antimatter annihilates on contact with normal matter, releasing all its energy instantly. You cannot store antimatter in a normal container. You need magnetic traps that suspend charged antiparticles away from container walls. Current magnetic traps can hold antiprotons for months, but scaling up to store kilograms of antimatter for decades presents challenges no one has solved. Exotic propulsion concepts like warp drives and wormholes remain firmly in the realm of speculation. General relativity, Einstein's theory of gravity, permits mathematical solutions involving faster-than-light travel through the manipulation of spacetime geometry. The Alcubierre drive concept proposes contracting space ahead of a spacecraft while expanding space behind it, creating a wave of distorted spacetime that carries the spacecraft faster than light relative to distant observers. The mathematics works, in the sense that the equations of general relativity permit such solutions. But realizing these solutions requires negative energy densities that may not exist in nature. Negative energy means energy less than the vacuum, a concept that quantum mechanics permits in limited circumstances, but that has never been demonstrated at the scales required for spacetime engineering. The energy requirements for an Alcubierre drive, even in optimized theoretical designs, exceed the mass energy of Jupiter. Converting an entire Jupiter-mass planet into pure energy to fuel a single spacecraft would represent engineering beyond anything humans can currently conceive, and we do not know how to create negative energy at all, much less in quantities measured in planetary masses. Wormholes, theoretical tunnels through spacetime that could connect distant locations, face similar obstacles. Creating a traversable wormhole would require exotic matter with negative mass, a concept that may be physically impossible. Even if such matter exists, stabilizing a wormhole against collapse would require threading it with matter that violates known physics. The concepts make fascinating science fiction, but offer no pathway toward actual interstellar transportation. The honest assessment of interstellar travel prospects is humbling. With any technology humans currently understand, reaching Proxima b within human-relevant timescales requires resources, energy, and engineering capabilities that exceed current civilization by factors of thousands or millions. We might eventually develop such capabilities. We might eventually launch missions to nearby stars, but this eventuality lies decades or centuries in the future, not years. And even if we could reach Proxima b, what would we find? A world bathed in lethal radiation from a flare star that erupts unpredictably and violently. A world locked in tidal embrace with its parent star, one hemisphere burning under eternal illumination and one hemisphere frozen in eternal darkness. A terminator zone of perpetual twilight, where hurricane-force winds, extreme temperature gradients, and constant atmospheric violence make surface habitability essentially impossible for any life form we can imagine. A planet that represents the universe's closest approach to habitable, while still falling catastrophically short of actual habitability. This is the final line we must not cross, the line between hope and reality, the line between what we wish Proxima b could be and what physics dictates it actually is, the line between dreams of interstellar colonization and the brutal mathematics of cosmic distance. Proxima b exists. This fact alone carries scientific significance. Rocky planets form around red dwarf stars, which means rocky planets form around 70% of all stars in our galaxy. Habitable zones contain worlds, which means billions of planets orbit at distances where liquid water could theoretically exist. The galaxy may teem with planets that, under better circumstances, could support life. Proxima b demonstrates that planet formation operates efficiently even around the smallest, coolest stellar furnaces. But Proxima b does not exist for our benefit. It does not exist as a backup home for humanity. It does not exist as a destination for interstellar colonists. It exists as a frozen, irradiated rock orbiting a violent stellar remnant, separated from Earth by distances that mock our technological ambitions. The announcement of Proxima b's discovery in 2016 triggered a wave of optimism that fundamentally misrepresented scientific reality. Media coverage emphasized possibility while downplaying obstacles. Public imagination filled in details that observations could not provide. A narrative emerged of Earth 2.0 waiting just beyond our reach, ready to receive humanity when we finally developed the technology to arrive. This narrative was false. It was always false. The scientific papers describing Proxima b contained warnings that headlines ignored. The planet's location in the habitable zone said nothing about its actual habitability. The parent star's activity ensured that surface conditions would prove hostile beyond any reasonable mitigation strategy. 7 years later, we know more about Proxima b and Proxima Centauri than we did at discovery. Each new observation has reinforced the pessimistic assessment rather than the optimistic one. The star is more active than initially measured, producing more frequent and more energetic flares than early studies suggested. The radiation environment is harsher than models predicted, with X-ray and ultraviolet fluxes that would sterilize any exposed surface. The planet's atmospheric retention is more problematic than optimists hoped, with models suggesting that billions of years of stellar activity have stripped away any primordial atmosphere. Proxima b has become a case study in the gap between astronomical discovery and practical habitability. Finding a planet is relatively easy with modern technology. Radial velocity measurements and transit observations have revealed thousands of exoplanets around nearby stars. But determining whether any particular planet could support life requires observational capabilities we do not yet possess. We cannot image exoplanet surfaces directly. We cannot measure their atmospheric compositions with precision. We cannot detect biosignatures that would indicate the presence of life. Reaching those planets to confirm ground truth exceeds human technology by margins we cannot currently quantify. The gap between detecting a planet and standing on its surface spans technological generations, perhaps technological eras. We might develop interstellar travel capability eventually, but eventually is not a timeline that helps us evaluate whether Proxima b could serve as a refuge for humanity. The line we must not cross ultimately refers to the boundary between scientific enthusiasm and scientific rigor. We crossed that line when we celebrated Proxima b as a potential second home. We crossed it when we imagined colonies in the Terminator zone. We crossed it when we treated the habitable zone as synonymous with habitable. Pulling back from that line requires accepting uncomfortable truths. The universe is hostile to life. The conditions that permit complex biology to exist represent a narrow range within a vast parameter space of possibilities. Habitable planets may be rare even within habitable zones. Interstellar distances may be permanently uncrossable, with any technology consistent with known physics. Humanity may be alone, or effectively alone, in a cosmos too vast and too empty for meaningful contact with any neighbors that might exist. But accepting these truths does not require abandoning hope. It requires redirecting hope toward achievable goals. We can study Proxima b using telescopes that will come online in coming decades. The extremely large telescope, currently under construction in Chile, will have sufficient resolution to potentially detect atmospheric signatures from nearby exoplanets. The James Webb Space Telescope is already revolutionizing our understanding of exoplanet atmospheres. Future missions might directly image nearby worlds, revealing surface features and atmospheric compositions. We can search for better candidates around more stable stars. Proxima b orbits a flare star, one of the most active red dwarfs in our stellar neighborhood. Other red dwarfs are quieter, less prone to the violent outbursts that sterilize nearby planets. And beyond red dwarfs lie sun-like stars, more distant but potentially hosting planets more similar to Earth in their stellar environments. We can develop technologies that might eventually, in centuries rather than decades, enable missions to nearby stellar systems. Even if we cannot reach Proxima b within lifetimes of anyone alive today, our descendants might develop capabilities that exceed our current imagination. The gap between us and interstellar travel is vast, but human technology has crossed vast gaps before. Proxima b taught us something valuable despite its hostility. It taught us that the universe does not provide backup planets on convenient timescales at convenient distances. It taught us that habitable zones are statistical constructs, not guarantees of habitability. It taught us that cosmic proximity by astronomical standards still implies distances beyond human practical reach. The line you must not cross on Proxima b is literal and lethal. Cross from the terminator zone toward the day side, and you face temperatures that would boil your blood within seconds. Cross toward the night side, and you face temperatures that would freeze it solid almost instantly. Remain in the terminator zone, and you face winds that would tear apart any structure we could build, temperatures that fluctuate with every stellar flare, and radiation that would penetrate any practical shelter. But the line you must not cross is also metaphorical and methodological. Cross from realistic assessment to wishful thinking, and you lose the ability to plan meaningful exploration. Cross from scientific evidence to popular narrative, and you mislead the public about humanity's cosmic options. Cross from hope grounded in physics to hope grounded in fantasy, and you guarantee eventual disappointment when reality reasserts itself. Proxima b represents the closest exoplanet in any star's habitable zone. It will likely hold this distinction for decades or centuries, until we develop detection methods capable of finding closer candidates, which may not exist within our stellar neighborhood. As such, Proxima b serves as a benchmark for what habitable zone means in practice. Our nearest potentially habitable neighbor is a radiation-blasted, tidally locked nightmare orbiting a violent flare star. If this represents the best the local universe offers, then the search for life beyond Earth faces challenges we have barely begun to comprehend. The optimistic assumptions that underlie many calculations of cosmic habitability may need revision in light of what Proxima b has taught us. Yet we continue searching. We continue building better telescopes. We continue developing better detection methods. We continue hoping that somewhere, some distance farther than Proxima b, a truly habitable world awaits discovery. This hope is not fantasy if it remains grounded in realistic assessment of both possibilities and obstacles. This is the appropriate response to Proxima b's harsh reality. Not despair, but determination. Not fantasy, but focused effort. Not crossing lines into wishful thinking, but maintaining rigorous assessment while pursuing long-term goals that might eventually yield better results. Proxima b is not what you think. It never was. The promise that fooled a planet in 2016 has given way to scientific understanding that reveals a hostile world beyond any reasonable hope of habitability or colonization. The artist's conceptions of blue oceans and green continents were fantasies. The headlines about Earth's twin were misleading. The optimism about backup planets was premature. The line you must not cross stands as a reminder. The universe does not bend to human desires. Physics operates according to its own rules, indifferent to our hopes and dreams. The cosmos extends in all directions, vast and empty, and mostly hostile, with occasional islands of warmth and light that may or may not harbor life. Earth remains our only confirmed habitable world. Proxima b, despite its proximity and its position in the habitable zone, cannot serve as a backup. The line between our world and that world measures 4.2 light-years of cold vacuum, and every kilometer of that distance reinforces our dependence on the fragile blue sphere we call home. This is the truth of Proxima b. This is the reality behind the headlines. This is what awaits anyone who imagines crossing the cosmic abyss to reach our nearest stellar neighbor. The line you must not cross is every kind of boundary at once. Physical distance that exceeds any technology we possess. Technological limitations that may persist for centuries. Biological requirements that Proxima b cannot meet. Psychological barriers between hope and evidence that we struggle to maintain. It separates Earth from a universe that, for all practical purposes, remains beyond human reach. Not forever, perhaps, but certainly for now. And probably for generations to come. Proxima b exists. We found it, we studied it, we learned from it, and we must accept that finding it and reaching it are challenges separated by chasms that current human capability cannot bridge. The closest potentially habitable exoplanet is not habitable. The nearest candidate for a second Earth is nothing like Earth. The world we hoped might someday receive human colonists would destroy any human who attempted to survive on its surface. Proxima b is exactly what physics predicts it should be: a rocky world in a habitable zone around a red dwarf, battered by stellar activity that sterilizes its surface, locked in eternal twilight that creates impossible temperature extremes, isolated by cosmic distances from any world that could send explorers to investigate. This is reality. This is what the universe provides when we ask for a nearby habitable world. This is Proxima b, the line you must not cross.